Reality might be the universe's greatest illusion. We are about to embark on a journey through 50 of the most bizarre space theories ever conceived, each one a mind-bending challenge to everything we think we know. By the end, you will see the cosmos not as a fixed stage, but as a collection of profound and unsettling mysteries. What if our universe is just a line of code in an alien supercomputer, or a holographic projection from the edge of nothingness? We will explore ideas so strange they feel like science fiction, yet are grounded in the cutting edge of theoretical physics. What single assumption about your existence are you most prepared to question? This idea is not a modern fantasy. The philosopher Nick Bostrom formalized a startling argument that one of three propositions must be true. Either civilizations inevitably go extinct before reaching a technological stage capable of creating simulated realities, or advanced civilizations have zero interest in running such simulations, or we are almost certainly living in one right now. Given the vast stretches of cosmic time and the potential for countless civilizations to arise, the third option begins to look statistically plausible. We could be digital ancestors in a universe built by our post-human descendants. The evidence, or the lack of it, might be hiding in plain sight. Quantum mechanics, with its particles that exist in multiple states until observed, feels eerily like a processor conserving resources, only rendering the details when someone is looking. Those strange cosmic coincidences, the fundamental constants fine-tuned just right for life, could be the initial parameters chosen by the programmer. And what of the glitches? Some scientists seriously propose we should search for signatures of a simulation, like subtle pixelation in the fabric of spacetime or anomalies in high-energy cosmic rays that reveal the underlying code. If this theory is true, then every star, every planet, and every conscious thought is part of an unfathomably complex calculation running on a computer in a base reality we can scarcely comprehend. The unsettling possibility of a simulated reality finds a strange cousin in an even more radical idea. This theory suggests our three-dimensional world, with all its depth and solidity, is not the fundamental reality. Instead, it proposes that everything we see and feel, every galaxy and grain of sand, is actually a projection from a two-dimensional surface at the very edge of the cosmos. We are living inside a cosmic hologram. The roots of this mind-bending concept come from an unexpected place, the study of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He found that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume as you might expect. It is proportional to the surface area of its event horizon. This was a profound clue. It hinted that all the information describing everything that ever fell into a black hole was not lost inside its three-dimensional core, but was somehow painted onto its two-dimensional boundary. Decades later, physicist Leonard Susskind and others expanded this into a full-blown principle. The holographic principle states that all the information contained within any region of space can be fully described by the physics on the boundary of that region. Think of a security hologram on your credit card. It is a flat, two-dimensional surface, but when light hits it just right, it projects a stunningly realistic three-dimensional image that seems to have depth and volume. In this analogy, our entire universe is that shimmering three-dimensional projection. The true reality, the equivalent of the flat sticker on the card, exists on a distant, two-dimensional surface we could never perceive directly. If this is true, then every event in your life, every memory and sensation, is merely a translation of data encoded on the cosmic horizon. The solidity of the floor beneath your feet, the vast emptiness of space, all of it is an incredibly convincing illusion generated by information processing on a flat screen at the edge of everything. This is not mere philosophy. scientists are actively looking for evidence, searching for a fundamental graininess or pixelation in spacetime that would betray its holographic nature. It suggests that the universe is not a container for information, but that information itself is the universe, with matter and energy simply being its most vivid expression. If information is the true fabric of reality, then what is the origin of a single, solitary thought? The holographic universe suggests we are projections of a grand cosmic code, but the Boltzmann brain paradox asks a far more intimate and disturbing question. Could you, the conscious entity having this thought right now, be nothing more than a fleeting accident? This is not a theory about the universe's structure, but a nightmarish thought experiment that emerges from our most fundamental laws of physics. It is named for Ludwig Boltzmann, a 19th-century physicist who helped develop our understanding of entropy, the natural tendency of systems to move from order to disorder. In an infinitely old and vast universe, the laws of probability suggest that even the most wildly improbable events must happen eventually. Given enough time and space, random quantum fluctuations could, by sheer chance, assemble a fully formed, self-aware brain, complete with a lifetime of false memories floating in the void. This brain would believe itself to be a person with a past, living in a real world, when in fact it is just a momentary bubble of order in an endless sea of chaos. It would think its experiences are real, just as you believe yours are right now. The paradox cuts to the heart of cosmology. Our universe is remarkably ordered, with low entropy in the distant past, which set the arrow of time pointing forward. But why was it so ordered to begin with? If a state of maximum disorder is the most probable, then it is vastly more likely for a single, isolated brain to fluctuate into existence than for an entire, ordered cosmos like ours to do so. Statistically, you should be a Boltzmann brain, not a person embedded in a consistent universe with billions of years of history. This is not a proposal anyone believes is true, but its very absurdity is a profound philosophical problem. It highlights a crisis in our reasoning. If our best theories of an eternal, inflationary cosmos inevitably predict that Boltzmann brains should outnumber normal observers like us by an unimaginable factor, then those theories might be fundamentally flawed. The paradox forces scientists to search for a cosmological model that naturally explains why we find ourselves in a structured universe and not as transient ghosts in an eternal night. It asks us to question the reliability of our own memories and observations. After all, if you were a Boltzmann brain, you would have no way of knowing it. Every piece of evidence you could possibly examine, from the fossil record to the light of distant stars, would simply be part of the elaborate, false memory implanted in that single, accidental moment of existence. This is the ultimate solipsistic nightmare, where the observer is the only real thing, and the entire cosmos is a convincing but utterly fake backdrop. The terrifying possibility of being a fleeting accident in the void gives way to a concept that feels like its explosive opposite. If black holes are the universe's ultimate drains, then white holes are its impossible fountains. They are the theoretical exit, the place where everything a black hole swallows might be violently reborn. The mathematics of Einstein's theory of general relativity, the very same equations that predict black holes, also allow for a solution describing a white hole. It is a region of spacetime that nothing can enter, only escape from. Imagine trying to swim up a waterfall that defies all gravity, where matter and energy erupt outward with irresistible force. While a black hole's event horizon is a point of no return for anything falling in, a white hole's horizon is a point of no admission for anything outside. It is a cosmic one-way door swinging only outward. This symmetry in the math is beautiful, but it creates a profound puzzle. If the equations allow them, where are they? We have overwhelming evidence for black holes, from stellar remnants to the supermassive beasts at galactic centers, but not a single confirmed observation of a white hole exists. One compelling idea is that a white hole is what a black hole becomes in the far, far future. Some models suggest that after a black hole has evaporated through Hawking radiation over unimaginable eons, its final act could be a transformation, a rebound into a white hole that releases the information it once consumed. Another, even more staggering hypothesis is that our own Big Bang was the ultimate white hole event, the cataclysmic eruption of an entire universe from a singularity in some parent cosmos. In this view, every universe might be born from the white hole of a dying black hole in another reality, creating an endless chain of cosmic reproduction. The reason we may never see one is that white holes are likely incredibly unstable, perhaps lasting for only a fleeting moment before collapsing or transforming. Or they could exist in regions of spacetime so radically warped that they are completely cut off from our observational reach. Their existence challenges our understanding of cause and effect, presenting a universe where creation can spring from destruction, and where every ending might secretly be a new beginning in a place we can never see. Yet if white holes offer a chaotic rebirth, another theory proposes a universe with perfect cosmic rhythm. The Big Bounce suggests our cosmos is not a one-time event, but merely the latest chapter in an endless cycle of expansion and contraction. Forget a definitive beginning or a lonely heat death. This is the universe as a cosmic heartbeat. In this model, the story does not end with galaxies drifting apart into cold, eternal darkness. Instead, the outward rush of expansion eventually slows, halts, and reverses. Driven by gravity, all matter and energy begin a long, slow collapse back toward a single point. Every star, every planet, every atom is pulled together in a cataclysmic convergence known as the Big Crunch. This is not an end, but a transformation. The universe is compressed into an incredibly hot, dense state, a singularity remarkably similar to the one from which our Big Bang erupted. And from that state, rebounding with unimaginable force, a new Big Bang occurs, birthing a fresh universe from the ashes of the old. This cycle of expansion, contraction, and rebirth could have been repeating for eternity, with each new universe inheriting and perhaps slightly altering the physical laws of its predecessor. This idea stands in stark contrast to the prevailing view of a one-way trip toward heat death, where the universe expands forever, stars burn out, and all activity grinds to a permanent halt in a state of maximum entropy. The cyclic model offers a comforting, even poetic alternative, a universe without true death, only perpetual renewal. But for the Big Bounce to be possible, our current understanding of dark energy presents a formidable challenge. Dark energy is the mysterious force causing the expansion of our universe to accelerate, pushing galaxies apart at an ever-increasing rate. For a big crunch to occur, this acceleration must eventually be overcome by the collective pull of gravity. Some cyclic models propose that dark energy is not a constant force, but one that weakens over time, or that it will eventually reverse its effect, acting as a catalyst for contraction. Others suggest that each bounce resets the cosmic clock, with dark energy playing a different role in each new cycle. While evidence currently favors an accelerating expansion, the ultimate fate of the cosmos remains one of physics' greatest open questions. The Big Bounce transforms our universe from a solitary tragedy into an endless epic, where every ending is merely a prelude to a new beginning, and where the cosmos itself breathes in an infinite, majestic rhythm. The comforting rhythm of a cosmic heartbeat gives way to a far more violent finale. While the Big Bounce offers renewal, another hypothesis presents an ending so absolute it defies imagination. This is the phantom energy hypothesis, a theory that takes the mysterious force of dark energy and pushes it to its most terrifying extreme. We currently observe dark energy as a gentle but relentless pressure accelerating the expansion of our universe. Phantom energy is its monstrous cousin, a form of dark energy with a negative pressure so powerful that its strength actually increases over time. Instead of merely pushing galaxies apart, phantom energy would cause the expansion of the universe to accelerate at an ever faster, exponential rate. The consequences are not just separation, but total annihilation in an event cosmologists call the Big Rip. The timeline of this apocalypse is as methodical as it is horrifying. First, the acceleration would overcome the gravitational glue holding clusters of galaxies together. Billions of years from now, these vast island universes would be shredded, their member galaxies flung into the ever-widening void. Next, the force would turn inward. The gravitational bonds within individual galaxies, like our own Milky Way, would be torn asunder. Stars would be ripped from their orbits, sent careening into the growing emptiness. As the phantom energy grows still stronger, it would target solar systems. Planets would be stripped from their suns. Then, it would confront the forces holding matter itself together. In the final moments, perhaps an hour before the end, the phantom energy's grip would exceed the forces binding individual planets and stars. Earth would be vaporized along with every other celestial body. Minutes later, molecules and atoms would be torn apart. In the last inconceivable fraction of a second, the very fabric of spacetime itself would be stretched to infinity, ripping apart the building blocks of reality, atomic nuclei, and the quarks within them. The universe would not end with a whimper of cold darkness, but with a silent, instantaneous scream as spacetime itself is shredded. Is there any evidence for such a cataclysm? Observations of distant supernova and the cosmic microwave background currently tell us dark energy behaves like a constant force, not the growing phantom. Yet, the data still allows for the possibility that dark energy could evolve into this phantom state in the distant future. The hypothesis remains a stark warning from the equations of cosmology, a reminder that the universe's ultimate fate may not be a slow fade, but a sudden and total disintegration of everything that ever was. The absolute destruction of the Big Rip leaves no room for anything else, or so it seems. Yet there is a concept so vast it makes even the end of one universe feel like a local event. This is the multiverse, and its simplest form is already written into the equations of our own cosmology. If the universe is truly infinite in extent, and the laws of physics are uniform everywhere, then something inevitable and astonishing must occur. In an endless expanse with a finite number of ways to arrange particles, every possible configuration must repeat, not just once but an infinite number of times. This is level 1 of physicist Max Tegmark's multiverse classification, and its implications are deeply personal. It means that somewhere in a galaxy identical to our Milky Way, orbiting a star identical to our Sun, is a planet identical to Earth. On that planet, there is a person who looks exactly like you, reading a script exactly like this one. But that is just the beginning. In another region of this infinite cosmos, there is an Earth where you made a different choice this morning, where a single coin flip landed on the other side, where every tiny variation that could have happened did happen. Somewhere you are a celebrated artist, somewhere else you never existed at all. This is not science fiction, but a direct mathematical consequence of an infinite, uniform universe. The space beyond our observable horizon, the part of the cosmos whose light has not had time to reach us in the universe's 13.8 billion year history, is likely staggeringly vast. If it is truly infinite, then these duplicate regions are not just possible, they are statistically guaranteed. The distances involved are mind-numbing, placing your nearest identical copy so far away that you could never, even in principle, communicate or travel to confirm their existence. They are forever beyond our cosmic event horizon. This idea transforms infinity from an abstract concept into a mirror maze of reality. It suggests that every life that could be lived is being lived an infinite number of times over. Every tragedy and every triumph, every mundane moment and every historic event is playing out on countless stages across the endless dark. It challenges our sense of uniqueness, placing our entire narrative as just one copy in an infinite library of variations. And if this first level feels expansive, it is merely the simplest layer of a much stranger and more layered cosmic possibility. An infinite cosmos filled with copies of ourselves is only the first layer of the multiverse. The next level introduces a reality where not just the arrangement of matter changes, but the very laws of physics themselves. This is the Level 2 multiverse, or the inflationary bubble universe model, and it emerges from our leading theory of the universe's first moments, cosmic inflation. Imagine a vast, eternally bubbling cosmic foam, a seething sea of pure energy. In this primordial froth, random quantum fluctuations can trigger a runaway process. A tiny patch of this foam suddenly undergoes a violent, exponential expansion, inflating faster than the speed of light and cooling as it stretches. That single bubble inflates into an entire universe like ours, with its own distinct set of physical laws and constants frozen into place as it cools. But here is the crucial point: that eternal background foam never stops bubbling. Countless other patches are inflating at different moments, each birthing its own separate cosmos. Our entire observable universe is just one bubble in an endless, frothing ocean of universes, a multiverse of cosmic bubbles. Each of these bubble universes is entirely disconnected from the others, separated by unimaginable stretches of still inflating space that acts as an impenetrable barrier. They are like separate soap bubbles floating in a vast, expanding foam, each with its own internal physics. In one bubble, the force of gravity might be 1,000,000 times stronger, making stars burn out in a blink. In another, the nuclear forces might be too weak to allow atoms to form at all, leaving a universe of scattered particles. Some bubbles might be stillborn, collapsing instantly. Others might be barren, with laws that never allow for complexity. Our universe, with its seemingly fine-tuned constants that permit galaxies, planets, and life, is simply one lucky ticket in an infinite cosmic lottery. This elegantly solves the puzzle of why our physics seems so perfectly calibrated for our existence. There is no fine tuner. We just happen to live in one of the rare bubbles where the numbers came out right. The theory even suggests a way we might find evidence. If two bubble universes collided in the distant past, the impact could have left a bizarre imprint on the cosmic microwave background, a strange circular pattern of hotter or colder temperatures. Astronomers have actually searched for these signatures, and while no definitive evidence has been found, the hunt itself shows this is more than just philosophy. It is testable science, painting a picture of a reality so vast that our entire cosmic history is just a local event in an endless, frothing sea of creation. But what if every choice at its most fundamental level literally splits the world in two? The bubble universes of cosmic inflation are separate creations, but the third level of the multiverse is born from the heart of reality itself, from the bizarre rules that govern the smallest particles. This is the quantum many-worlds interpretation, and it proposes that our universe is constantly forking into countless new versions of itself. In the 1950s, a young physicist named Hugh Everett was deeply troubled by the prevailing explanation of quantum mechanics. The Copenhagen interpretation said that particles exist in a blurry cloud of possibilities, a superposition, until the moment they are observed. Then, the wave function collapses and the particle picks a single, definite state. Everett asked a simple, radical question: what if the wave function never collapses at all? What if every single possible outcome actually happens? His answer was that the universe itself splits. At every quantum event where multiple outcomes are possible, reality divides like a branching path. Each possibility plays out, but in a newly created parallel universe. The famous thought experiment of Schrödinger's cat is the perfect illustration. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, releasing the poison and killing the cat. According to quantum rules, until the box is opened, the atom is in a superposition of both decayed and not decayed. The Copenhagen interpretation says the cat is therefore both dead and alive, a blur of possibilities until an observer looks inside and forces a single reality. Everett's many worlds interpretation offers a very different and somehow more unsettling resolution. At the moment the quantum event occurs, the universe splits. In one new branch, the atom decayed, the poison was released, and the cat died. In the other equally real branch, the atom did not decay, and the cat lives on. Both realities exist, but they have decohered, becoming separate, non-interacting threads in the vast tapestry of the multiverse. There is no single, privileged outcome, and no mysterious collapse caused by consciousness. There is only endless, continuous branching. Every time an electron spins in two possible directions, the universe splits. Every time a photon could go left or right in an experiment, it goes both ways in two new worlds. This means that for every decision you have ever made, even the smallest one, there is a version of you in another branch who made the other choice. The philosophical weight of this is staggering. It suggests that every tragedy was averted somewhere else, that every missed opportunity was seized in another reality. It removes probability from the fabric of the world and replaces it with absolute certainty. Every possible thing that can happen does happen in some branch of the multiverse. The reason we only experience one timeline is that our consciousness itself splits, following just one path on the ever-dividing tree. We are not the authors of a single story, but merely readers on one of infinite, constantly multiplying pages. The endless branching of quantum worlds still operates within a framework of space, time, and physical law. But what if even those are just subsets of something far more fundamental? This brings us to the fourth and most profound level of the multiverse, the mathematical universe hypothesis. Proposed by physicist Max Tegmark, this is the ultimate claim that reality is mathematics. Not just described by it, but that it is mathematics. Tegmark argues that any structure that can exist within a self-consistent mathematical framework does exist physically in its own universe. Our cosmos, with its three dimensions of space, one of time, and its specific set of particles and forces, is simply one particular mathematical structure. It is the set of equations that describe our physics, and we are patterns within that computation. Think of it this way. A circle is a mathematical object defined by a set of points equidistant from a center. That abstract idea exists independently of anyone drawing it. Tegmark takes this Platonist view to its extreme. He suggests that every possible mathematical object, from the simple geometry of a dodecahedron to the incredibly complex equations of a universe with 17 dimensions and 5 fundamental forces, corresponds to a real, physical reality somewhere in the ultimate multiverse. In this view, the reason our universe seems so mathematical is not because we are clever at finding patterns, but because it is literally made of math. The particles are not little balls being pushed around by fields, they are solutions to equations. Spacetime is not a container, it is a geometric shape. Consciousness itself might be a particular type of complex information processing pattern within a specific mathematical structure. This idea dissolves the boundary between the abstract and the concrete entirely. A universe governed by entirely different laws is not just a different arrangement of matter in some distant bubble, it is a different equation altogether. Some of these mathematical universes would be barren and simple, perhaps containing only static, eternal shapes. Others might be buzzing with complexity and forms of life we could never recognize based on logic we cannot fathom. This hypothesis answers, or perhaps sidesteps, the deepest question of all. Why is there something rather than nothing? Because in the realm of all mathematical possibilities, nothingness is just one particular and very boring structure. The existence of our rich universe is no more mysterious than the existence of the number 4. It simply is because it can be. While this is arguably the most speculative level, it is also the most complete. It encompasses all the others. An infinite space with repeating regions is one mathematical structure. Bubble universes with different constants are another set of equations. The branching quantum worlds are a specific mathematical formalism describing endless splitting. They all become subsets of the level 4 multiverse, special cases within the infinite library of all possible mathematical realities. It presents a cosmos where imagination and discovery are the same thing, and where every consistent story, no matter how bizarre, is being told somewhere in the vast, silent pages of mathematical existence. Mathematics may be the ultimate reality, but our own universe has a very specific and violent origin story. We call it the Big Bang, a singularity from which all space, time, and matter erupted. But singularities are not unique to cosmic beginnings. We find them at the heart of black holes, the ultimate endpoints of gravitational collapse. This symmetry has led to a breathtaking and strangely elegant proposal. What if our Big Bang was not a unique creation event, but simply the interior of a black hole in a much larger parent universe? In this theory, our entire cosmos exists inside the event horizon of a colossal black hole. When a massive star collapses at the end of its life, it forms a stellar black hole. But what if, in some unimaginably vast parent cosmos, an object of even greater scale underwent gravitational collapse? The mathematics suggests that as matter falls toward the singularity at a black hole's center, from the perspective of that infalling matter, something remarkable happens. Time and space swap roles. The radial direction inward toward the singularity becomes a direction of time, not space. This means that to an observer hypothetically falling inside, the singularity is not a place in their future, but a moment in their past. From their point of view, looking outward, they would see an expanding universe with a beginning in time. This is precisely what we observe from our vantage point. Our cosmic past is a hot, dense state, a singularity. Could that be the moment of our parent black hole's formation? In this model, the Big Bang is not an explosion into a pre-existing void. It is the birth of a new space-time geometry from the collapse of matter in another reality. The event horizon of that parent black hole becomes our cosmic horizon, the limit of what we can see. Everything we observe, every galaxy racing away from us, is contained within this bounded region. This idea offers potential solutions to some of cosmology's deepest puzzles. It could explain the origin of the Big Bang's singularity without invoking a true beginning of everything. It also provides a natural home for all the information that falls into a black hole. The information paradox asks what happens to the detailed data of matter consumed by a black hole if the black hole eventually evaporates via Hawking radiation. If our universe is inside a black hole, then that information is not lost. It becomes the initial conditions, the very seed from which our entire cosmic history unfolds. The stars, planets, and people of our universe could, in a very real sense, be a transformed re-expression of the information that collapsed to form our parent black hole. We are not just in a universe, we might be the interior of a cosmic tomb that is, for us, a cradle. This theory suggests a nested reality where black holes are not just destructive pits but portals to new creation. Every black hole in our universe could, in turn, contain an entire cosmos within it, a fractal chain of universes birthing universes. It paints a picture of existence as an infinite Matryoshka doll, where we live inside one layer of an endless, dark inheritance. Nested within a black hole or not, our universe's violent birth is a central mystery. But what if the Big Bang was not a singular explosion but a cosmic crash? This is the ekpyrotic universe model, a theory that replaces the fiery singularity with a collision of ghostly, higher dimensional sheets. The name itself comes from the ancient Greek word for conflagration, yet the process it describes is remarkably smooth and cold. In this radical picture, our familiar three-dimensional universe is not all there is. It is a three-dimensional membrane, or brane for short, floating within a hidden, higher-dimensional space called the bulk. Think of our universe as a single, vast sheet of paper existing alongside other, parallel sheets in a grand, multidimensional stack. For most of eternity, these branes float peacefully in the bulk, parallel to one another but not touching. Then, drawn together by a faint force across the higher dimension, they begin to move, slowly at first, then with gathering inevitability, two of these cosmic sheets drift toward each other. When they finally meet, they do not pass through one another. Instead, they collide. That collision, that moment of contact across the full expanse of each brane is our Big Bang. The immense kinetic energy of the impact is converted instantly into the heat, radiation, and matter that would fill the newborn cosmos. This model offers a dramatic alternative to the standard inflationary Big Bang. In the classic view, the universe emerges from a point of infinite density and temperature, a singularity where our laws of physics break down. The ekpyrotic scenario has no such singularity. The branes themselves are cold and empty before the collision. The universe begins not with an incomprehensible fireball, but with a structured geometric event. This leads to a key prediction. A collision of smooth sheets should produce a universe that is itself incredibly smooth and flat from the outset, without the need for a period of hyper-fast inflation to iron out wrinkles. The cosmic microwave background, the afterglow of the Big Bang, should show a specific, subtle pattern of temperature variations different from those predicted by inflation. While current data from satellites like Planck slightly favors the inflationary model, the ekpyrotic idea remains a compelling and elegant contender. It transforms our origin from a mysterious eruption from nothing into a potentially cyclical story. After the collision, the branes might bounce apart, stretch, and eventually be drawn together again for another collision, birthing a new universe in an endless, rhythmic cycle of creation. It is a universe born not from a solitary scream, but from a silent, multidimensional embrace. From a cosmic collision, we turn to a structure that defies time's arrow. Time crystals are not science fiction. They are a bizarre new phase of matter that physicists have actually created in laboratories. Unlike ordinary crystals like diamonds or snowflakes, which have atoms arranged in a repeating pattern in space, a time crystal structure repeats in time. It oscillates between states in a perpetual, regular rhythm, not because it is storing energy like a clock, but because it is locked in a quantum dance that resists the natural tendency toward equilibrium. It is a system that breaks time symmetry, ticking forever without ever winding down, the closest thing to a perpetual motion machine the laws of physics might allow. Now, a handful of theorists have taken this strange idea and scaled it up to the absolute maximum. They propose that our entire universe could be a time crystal on a cosmic scale. In this view, the cosmos is not a static stage where events play out, but a dynamic, repeating pattern woven into the fabric of spacetime itself. The expansion and contraction of space, the dance of galaxies, even the flow of time as we perceive it, could all be part of an immense cyclical oscillation. This is not the big bounce of earlier cycles, but something more fundamental, a universe that is structurally periodic, its very existence defined by a timeless beat. If true, it would mean the universe has a kind of built-in clock, a master rhythm that underlies all other processes. The implications are staggering. It suggests a form of perpetual motion is not just possible, but is the default state of reality. Time itself would not be a smooth, flowing river from past to future, but a series of pulses or frames in a cosmic film reel. Our conscious experience of a linear timeline would be an emergent illusion, much like the illusion of a moving picture created by still images flashing quickly on a screen. This theory forces us to reconsider the nature of time at its deepest level. Is time a fundamental dimension, or is it merely a side effect of a universe stuck in an eternal, repeating groove? The search for evidence is profoundly challenging, but some scientists suggest that if the universe is a time crystal, there might be subtle imprints of its periodic structure on the cosmic microwave background, or strange correlations in the distribution of galaxies across the sky that hint at an underlying cosmic rhythm. It presents a universe that is not just evolving through time, but one that is, in its very essence, an expression of time. Our universe may be the ultimate student, learning its own laws as it grows. The neural network theory takes the idea of a digital or informational cosmos to a startling new level. It proposes that reality is not just like a computer, it is literally a vast cosmic-scale neural network, the same kind of architecture that powers modern artificial intelligence. In this view, every particle, every force, and even the fabric of spacetime itself emerges from the complex interactions of countless simple nodes, processing information and learning patterns in a way that creates the world we perceive. The architect of this idea, physicist Vitaly Vanchurin, suggests we might be living inside a machine that is teaching itself physics. A neural network, in its simplest form, is a web of interconnected nodes or neurons. Each connection has a weight, a strength that determines how much influence one node has on another. By adjusting these weights based on input data, the network can learn to recognize patterns, from identifying cats in photos to mastering complex games. The universe as a neural network would operate on a similar principle, but at the most fundamental scale imaginable. The nodes would not be silicon chips, but the most basic units of existence, perhaps existing at the Planck scale, the smallest meaningful size in physics. Their connections and the evolving weights between them would give rise to everything we see. In this framework, particles like electrons and quarks are not tiny billiard balls. They are stable patterns of excitation within the network, persistent signals that emerge from the chaotic flow of information. The forces of nature, like gravity and electromagnetism, are not fundamental fields but the rules of interaction between nodes, the algorithms governing how information is passed and transformed. Even time itself could be an emergent property, a record of the sequence of states as the network updates and learns. This is a form of digital physics where the universe is fundamentally discrete and computational. But it adds a crucial dynamic element: learning. The cosmic network might have started in a relatively simple, random state. Through a process akin to training, it has self-organized, adjusting its internal connections to minimize a kind of cosmic error, leading to the stable, structured, and mathematically elegant universe we observe today. The laws of physics are not inscribed on some celestial tablet. They are the habits the network has learned. This provides a breathtaking answer to why our universe is comprehensible at all. It is comprehensible because it is the output of a learning process that tends toward stability and pattern. The theory even suggests a way to test it. If the universe is a neural network, there might be a limit to how finely we can probe reality, a fundamental graininess or noise that appears at the smallest scales, like the pixelation of a digital image. It turns the mystery of existence into a question of machine learning, asking not why the universe is, but what it is trying to figure out. The universe may be learning its own rules, but its greatest student remains invisible. For decades, the hunt for dark matter has focused on hypothetical particles, weakly interacting massive particles or WIMP that barely touch normal matter. Yet despite immense effort and sophisticated detectors buried deep underground, these ghostly particles have never been caught. This persistent silence has revived a much older and far more dramatic candidate. What if dark matter is not made of unknown particles at all, but of ancient celestial corpses? This is the primordial black hole dark matter theory. It proposes that a vast population of small, incredibly dense black holes formed not from dying stars, but in the seething chaos of the universe's first second. In those initial moments of extreme density, random fluctuations could have caused pockets of space to collapse directly under their own gravity, stitching tiny singularities into the fabric of the cosmos before the first stars ever ignited. These primordial black holes could range in size from smaller than an atom to larger than a star, with the most promising candidates for dark matter being about the mass of a large asteroid compressed into the size of a proton. Such an object would be almost undetectable by conventional means, yet its gravitational pull would be immense. This idea elegantly solves several puzzles at once. It provides the invisible mass that binds galaxies and shapes the cosmos, and it does so with objects we already know exist, black holes, just of a different, more ancient breed. The search for them, however, is a cosmic game of shadows. Scientists look for a phenomenon called gravitational microlensing. If a primordial black hole drifts precisely between Earth and a distant star, its intense gravity will act as a lens, bending and focusing the star's light. For a brief period, that star will appear to mysteriously brighten, then fade as the black hole moves on. Teams have scanned millions of stars for these telltale flashes, and while a handful of intriguing events have been recorded, none yet provide definitive proof. The theory faces challenges, particularly from observations of the cosmic microwave background and the way dwarf galaxies hold together, which seem to constrain how many of these ancient black holes could exist. Yet it remains a powerful and haunting alternative, suggesting that the dark skeleton of our cosmos might be built not from exotic particles, but from the fossilized scars of creation itself, countless silent ghosts from the universe's violent birth. The silent ghosts of primordial black holes haunt the outer darkness, but a more tangible and perhaps closer mystery may be lurking in our own cosmic backyard. Far beyond Neptune, in the frigid expanse of the Kuiper belt, something massive appears to be pulling on the debris of our solar system. This is the Planet 9 hypothesis, the compelling case for a hidden world 10 times the mass of Earth orbiting in a vast elliptical path around our Sun. The evidence comes not from a direct photograph, but from the strange ballet of distant ice worlds. Astronomers have discovered a handful of small, icy objects in the Kuiper belt with orbits that are oddly clustered. Their closest approaches to the Sun, their perihelia, are grouped together in space, and their orbits are tilted in a similar direction. This clustering is statistically bizarre, like finding several scattered leaves all pointing north when the wind blows randomly. The gravitational influence of the known giant planets cannot explain this alignment. The most elegant solution is the gravitational hand of an unseen, super-Earth-class planet. Its immense pull over billions of years would have shepherded these smaller objects into their peculiar, grouped orbits. Visualize the solar system not as a flat disk, but as a dynamic sculpture. Planet 9's proposed orbit is a long, slow ellipse, taking perhaps 15,000 years to complete a single journey around the Sun. At its closest, it might come within 300 times Earth's distance from the Sun, still far beyond Neptune. At its farthest, it would vanish into the deep freeze, over 6 times that distance away. This world would be an ice giant shrouded in perpetual twilight, a dark mirror to Neptune, reflecting only the faintest glimmer of starlight. Where could such a giant have come from? It is unlikely to have formed in its current distant, lonely orbit. The leading theory suggests it was born much closer to the Sun, alongside the other giants, before a gravitational tug of war with Jupiter or Saturn flung it onto its extreme path. It is a cosmic castaway, exiled to the solar system's frozen frontier. The hunt for this phantom planet is one of astronomy's great modern quests. Teams are using the world's most powerful telescopes, like Subaru in Hawaii, to scan vast patches of sky where the planet's predicted orbit might lie. They are looking for a single, slow-moving point of light against the fixed background of stars. An incredibly challenging task given its predicted faintness and immense orbital timescale. Each new discovery of a distant Kuiper belt object with a skewed orbit refines the search area, tightening the net around this solar system ghost. Finding it would be a monumental discovery, rewriting the story of our planetary family and reminding us that even in our own celestial neighborhood, profound mysteries still await in the dark. A hidden companion to our Sun could be the solar system's most elusive predator. For decades, paleontologists have grappled with a disturbing pattern in Earth's fossil record. Major extinction events like the one that wiped out the dinosaurs seem to strike with a grim regularity, roughly every 26 to 30 million years. This cosmic clockwork demanded a cosmic explanation, and in 1984, two separate teams of scientists proposed a startling culprit. They theorized our Sun is not alone but part of a binary star system. Its companion, a small, dim red dwarf or a failed star known as a brown dwarf, was given a name straight from Greek mythology, Nemesis. This dark twin would orbit our Sun on a vast, elliptical path that takes it far into the icy reaches of the Oort cloud, a spherical shell of trillions of icy bodies surrounding our solar system. Every 26 million years or so, Nemesis makes its closest approach. Its gravitational influence acts like a wrecking ball swung through a field of delicate structures. As it plows through the Oort cloud, its gravity violently disturbs the orbits of countless dormant comets, sending a deadly shower of icy missiles hurtling inward toward the planets. Earth, moving through its orbit, would find itself in the crosshairs of this celestial bombardment. A single, large comet impact is enough to cause global catastrophe, as the dinosaur-ending Chicxulub impact proved. A period of sustained bombardment from a Nemesis-induced comet shower could explain not just one, but several of the periodic mass extinctions etched into our planet's geological history. The beauty of the theory was its testable prediction. Astronomers began searching the skies for this faint, distant object. They scanned infrared surveys looking for the telltale heat signature of a brown dwarf. They studied the precise motions of nearby stars, searching for any subtle wobble in the Sun's position that would betray the gravitational tug of an unseen partner. Yet, after decades of increasingly sensitive searches, Nemesis remains undetected. No star or brown dwarf matching its predicted profile has been found within the necessary distance. While the idea of a Death Star companion is captivating, the evidence has not materialized. Most astronomers now consider the Nemesis theory unlikely, attributing the perceived periodicity in extinctions to statistical noise or to other cosmic cycles, like our solar system's vertical oscillation through the crowded plane of the Milky Way galaxy, which might also disturb comets at regular intervals. Still, the ghost of Nemesis lingers. It represents a profound shift in perspective, forcing us to see our solar system not as a solitary, stable family, but as a potential double act with a dark, chaotic partner. It reminds us that the greatest threats to life on Earth may not come from within, but from the gravitational shadows cast by our own star's hidden kin. The search for a hidden companion star forces us to look outward, but perhaps the true master of cosmic motion lies at the very heart of everything. We have mapped supermassive black holes at the centers of galaxies, including our own Milky Way. Yet a far more radical proposal suggests this hierarchy continues upward to the ultimate scale. What if our entire universe, in all its vastness, orbits an incomprehensibly large black hole at its absolute center? This is not a black hole as we understand them within galaxies, but a cosmic singularity of such staggering proportions that its gravitational influence shapes the expansion of the cosmos itself. Proponents of this fringe theory look at the large-scale structure of the universe and see a pattern that hints at a central anchor. The observed expansion of space is uniform in all directions, but what if that expansion is not a property of empty space, but a dynamic effect created by our position relative to a central, universe-sized attractor? In this model, the Big Bang's outward rush could be reinterpreted as matter being flung away from this primordial, galaxy-swallowing pit, with the cosmological constant or dark energy being a manifestation of its lingering gravitational potential. This idea takes the concept of a great attractor, a mysterious gravitational anomaly pulling our local galaxy cluster, and scales it up to the ultimate extreme. Instead of a regional curiosity, the entire cosmos would have a true center, a location of infinite density where all paths ultimately lead. Every galaxy's recession in this view is part of a grand, slow-motion orbit around this central darkness. The cosmic microwave background, the afterglow of the Big Bang, presents the greatest challenge to this idea, as it appears remarkably uniform in all directions, suggesting no special center. Advocates counter by proposing complex geometries where the uniformity is an illusion of our perspective within the gravitational well, much like how the surface of the ocean looks flat from a boat despite the Earth being round. While firmly outside mainstream cosmology, this theory forces a profound philosophical question. We assume the universe has no center, that every point is equivalent. But what if that assumption is wrong? What if we are not in a featureless expanding loaf of raisin bread, but in a vast spinning whirlpool circling a drain of unimaginable scale? It suggests a cosmos with a true heart of darkness, a silent engine whose gravity we feel not as a pull, but as the very stretching of reality. The idea of a cosmic center is a search for external order, but what if the deepest mystery is not out there, but within us? The quantum consciousness theory makes a radical claim that our subjective experience, the very phenomenon of awareness, is not a product of classical brain chemistry alone, but arises from quantum processes happening inside our neurons. This is not just a new idea about the mind, it is a potential solution to one of physics' greatest puzzles, the observer effect in quantum mechanics. In the classic double-slit experiment, a particle like an electron fired at a barrier with two slits behaves as a wave, creating an interference pattern on the detector screen behind it. But the moment scientists place a measuring device to observe which slit the electron goes through, the wave-like behavior vanishes. The electron acts like a single particle. The baffling question has always been, what constitutes an observation? Does it require a conscious human being to look at the data? Some theorists, like Roger Penrose and Stuart Hameroff, propose that consciousness itself is the catalyst. Their or theory suggests that structures inside neurons called microtubules, tiny protein scaffolds, are the seat of quantum computation. Within these microtubules, quantum superpositions can form and persist long enough to influence neural activity. When these quantum states collapse, they generate moments of conscious experience. In this view, the mind is not a classical computer, but a quantum orchestra. This bridges the gap between the intangible world of quantum possibility and the concrete reality we perceive. Our observation of the world literally collapses quantum wave functions, bringing one specific reality into being from a sea of potentials. It suggests a profound entanglement, not just between particles, but between our minds and the fabric of the cosmos. We are not passive witnesses to a predetermined universe, we are active participants in its manifestation. The implications spiral outward. If consciousness is quantum, it might not be bound by the brain. It could be a fundamental feature of the universe, like space and time, with our brains acting as receivers or amplifiers rather than generators. This resonates with ancient philosophical ideas of a universal mind. The theory remains highly controversial, with many neuroscientists arguing the warm, wet, noisy environment of the brain is utterly hostile to delicate quantum coherence. Yet, if even partially true, it would mean the greatest frontier is not in the distant stars, but in the quantum depths of our own awareness, where the universe becomes conscious of itself. Consciousness could be the universe's way of observing itself, but who was here first to do the observing? The leap from quantum awareness to alien gardeners is not as vast as it seems. This brings us to a theory that reframes the origin of life on Earth not as a local accident, but as a deliberate delivery. Panspermia, the idea that life exists throughout the cosmos and can be spread between worlds, is provocative enough. But its directed version adds a staggering layer of intention. It proposes that life on our planet was no random contamination by a space rock. It was a purposeful act of cosmic agriculture, a seeding event orchestrated by an ancient intelligence. The building blocks of life, or perhaps even dormant microorganisms, were intentionally sent to Earth aboard a designed vessel when our young world was ripe for cultivation. This transforms our biological history from a solitary genesis into a chapter of a galactic or even intergalactic legacy. The evidence for such a fantastic idea is understandably elusive and hotly debated. Yet its proponents point to tantalizing mysteries. In August 1977, the Big Ear radio telescope at Ohio State University recorded a signal from deep space so powerful and unusual that the astronomer who discovered it, Jerry Amon, famously circled it on the printout and wrote, "Wow." Next to it, the signal lasted 72 seconds, matched the expected signature of an artificial transmission, and came from the direction of the constellation Sagittarius. It has never been detected again, despite numerous attempts. While natural explanations exist, like a comet's hydrogen cloud, its unique profile makes it a perennial candidate for a fleeting brush with an alien beacon, perhaps even a relic of the civilization that once seeded our corner of the galaxy. Then there are the interstellar visitors. In 2017, astronomers spotted an object unlike any other. Named Oumuamua, Hawaiian for scout, it was the first confirmed body from another star system to pass through our solar system. Its characteristics were bizarre. It had an elongated, cigar-like shape, showed no signs of outgassing like a typical comet, yet accelerated away from the sun in a way that could not be explained by gravity alone. While most scientists favor natural explanations, like it being a peculiar shard of nitrogen ice, its oddities led some, like Harvard astronomer Avi Loeb, to openly speculate it could be artificial debris, perhaps a light sail from a long-dead civilization. Could such objects be the discarded or dormant arcs of a directed panspermia program? The theory asks us to consider a new origin story. Instead of a lightning strike in a primordial soup, imagine a carefully targeted probe arriving billions of years ago, releasing its biological payload into Earth's early oceans. Our entire tree of life, from the simplest bacteria to the complexity of human consciousness, would then be the cultivated offspring of that ancient gift. This idea does not answer the ultimate question of how life began. It simply moves it elsewhere and adds a gardener. But it offers a profound and humbling perspective, suggesting we are not alone in our history and that our very existence might be part of a grand biological experiment spanning the stars. A cosmic fluid with two faces could rewrite the rules of the universe. For decades, cosmologists have wrestled with two separate and dominant mysteries: dark matter and dark energy. The first is an invisible glue holding galaxies together, while the second is a repulsive force tearing the cosmos apart. But what if these two colossal enigmas are not separate entities at all, but different manifestations of a single, unified substance? This is the radical proposal of the dark fluid theory. It suggests that a single, exotic cosmic medium permeates all of space, a fluid that can change its behavior depending on its environment. Within the dense, crowded neighborhoods of galaxies, this fluid acts like a heavy, sluggish substance, clumping together under gravity to provide the extra mass we call dark matter. Its presence explains why stars at the edges of galaxies orbit just as fast as those near the center, defying the predictions based on visible matter alone. Yet in the vast, nearly empty voids between galaxy clusters where matter is sparse, this same fluid undergoes a transformation. It becomes expansive and repulsive, generating the negative pressure that drives the universe's accelerating expansion, the effect we label dark energy. Imagine a single material that is both putty and spring. In your hands, you can mold it into a dense, heavy ball that holds its shape, but leave it alone on a table and it slowly, relentlessly expands, pushing everything away from its center. The dark fluid would be this cosmic chameleon, its properties dictated by the density of the space it occupies. This idea is more than just a convenient simplification. It is an elegant solution born from the mathematics of Einstein's theory of general relativity. The equations allow for the existence of such a substance, often modeled as a Chaplygin gas, a theoretical fluid with negative pressure. By unifying the dark sector, this theory elegantly trims the number of unknown components in our cosmic inventory. Instead of two separate, unexplained phenomena, we are left with one, albeit a profoundly strange one. The challenge, of course, is detection. How do you find a substance that is everywhere yet interacts with light and normal matter only through gravity? Scientists are looking for subtle signatures, such as precise measurements of how galaxy clusters evolve over time or minute distortions in the cosmic microwave background that a unified dark fluid would predict differently than separate dark matter and energy. If confirmed, it would mean we have fundamentally misunderstood the dominant components of reality, not as two opposing forces, but as two moods of a single, shadowy ocean in which all galaxies float. A unified dark fluid may be the universe's hidden ocean, but its fabric could be stitched with scars from creation itself. These are cosmic strings, hypothetical threads of pure energy thinner than a proton but stretching across the entire universe. They are not made of matter, but are thought to be one-dimensional cracks in space-time, relics of a phase transition in the cosmos's first moments, like the fissures that form in ice as water freezes. If they exist, they are the ultimate fossils, remnants of a time when all the fundamental forces of nature were one. A cosmic string would possess almost unimaginable density. A single inch of it could weigh as much as a mountain range. This extreme mass warps spacetime around it with such ferocity that it creates a lensing effect, distorting the light from galaxies behind it into double images. But the most mind-bending property of these strings is their potential to manipulate time itself. Because they are under immense tension, they vibrate at nearly the speed of light. According to Einstein's theories, if two cosmic strings were to move past each other at such incredible velocities, the spacetime around them would become so twisted that it could create closed time-like curves. In simpler terms, this could open a path to the past. An object traveling on a precise trajectory around the dancing strings could, in theory, return to its starting point before it ever left. While this is a far cry from a practical time machine, it reveals how the extreme geometry of the early universe could have written time travel into the very laws of physics. Beyond their temporal tricks, cosmic strings would be cosmic lighthouses for gravitational wave astronomy. Their violent vibrations and intersections would send powerful ripples through the fabric of spacetime, a constant hum of whispers from the universe's birth. Scientists are listening for this hum with instruments like LIGO and Virgo, searching for a background rumble distinct from the chirps of merging black holes. They are also scanning the skies for the telltale double images of distant galaxies, a signature of a string's gravitational lens. Finding even one cosmic string would be a direct window into the universe's first fractions of a second, confirming theories of grand unification and revealing a cosmos laced with defects of pure energy, where the scars of creation hold the keys to time and space. The universe's scars may allow for time travel, but nature itself might have a failsafe to prevent it. Stephen Hawking, ever the cosmic skeptic, proposed a brilliant and almost comforting idea he called the chronology protection conjecture. He suggested the laws of physics contain a built-in mechanism that actively prevents travel into the past, a cosmic sensor that stops paradoxes before they can ever happen. Hawking was deeply troubled by the implications of time travel, not as science fiction, but as a real possibility within Einstein's equations of general relativity. Solutions like wormholes or cosmic strings could, in theory, be manipulated to create closed time-like curves, paths that loop back on themselves. Yet if such journeys were possible, the logical contradictions would be catastrophic. Imagine going back in time and preventing your own birth. If you were never born, you could never go back in time to stop the event, creating an unresolvable loop of cause and effect. The universe, Hawking reasoned, would find such paradoxes intolerable. He believed that whenever conditions arise that could allow a time machine to form, something would always go wrong to stop it. Quantum effects would become dominant. Virtual particles swirling around the mouth of a wormhole would feed back on themselves with infinite energy, destroying the tunnel before it could be stabilized. The very act of trying to bend spacetime into a time loop would trigger a catastrophic release of radiation or a gravitational collapse, a self-correcting error in the cosmic code. In essence, the universe protects its own chronology, its orderly sequence of cause and effect, by making time travel to the past physically impossible. It is not a law written in a book, but an active enforcement, like a cosmic immune system that attacks temporal infections. This conjecture has never been proven, but it aligns with a profound intuition. Our experience of time as a one-way street with a clear past, present, and future may not be an illusion, but a fundamental and guarded feature of reality. The cosmos might simply refuse to let us break its most important rule. Hawking's cosmic sensor protects the timeline, but what if we could sidestep the speed limit entirely? The dream of faster-than-light travel is a cornerstone of science fiction, yet within the sober pages of general relativity, a backdoor exists. In 1994, physicist Miguel Alcubierre proposed a theoretical engine that would not push a ship through space, but would instead move space itself around the ship. This is the Alcubierre warp drive, a concept that turns the universe into a moving sidewalk. The design is deceptively simple in principle. Imagine a spacecraft sitting inside a bubble of flat, normal spacetime. Ahead of the ship, spacetime is powerfully contracted, pulling distant stars closer. Behind the ship, spacetime is dramatically expanded, pushing the starting point far away. The ship itself rests comfortably in the bubble, experiencing no acceleration forces, no time dilation, and crucially, never locally exceeding the speed of light. It is the bubble, the fabric of the universe, that moves, carrying the ship along like a surfer on a wave. This wave could, in theory, propagate at speeds vastly greater than light, allowing journeys to neighboring stars in weeks or months instead of millennia. The catch, and it is a monumental one, lies in the fuel. To create this warping of space-time, the Alcubierre drive requires a form of matter with negative energy density, often called exotic matter. This is not just rare or unknown material, it is substance that defies classical physics, possessing a gravitational repulsion rather than attraction. While quantum mechanics allows for fleeting instances of negative energy in phenomena like the Casimir effect, where two metal plates in a vacuum experience a slight attractive force due to virtual particles, the amounts needed for a warp bubble are astronomical. Early calculations suggested the energy equivalent of converting the mass of Jupiter into pure negative energy, an utterly impossible feat. Yet the story does not end there. In the years since, theoretical refinements have offered glimmers of hope. Researchers have found that by shaping the warp bubble into a torus or donut shape, the negative energy requirements could be reduced from a planetary mass to perhaps merely a mass equivalent to a small spacecraft. Other studies suggest that manipulating the bubble's geometry or oscillating its walls could lower the barrier further. While still firmly in the realm of theory, these mathematical explorations keep the dream alive. They hint that the laws of physics might not forbid faster-than-light travel outright, they just make it extraordinarily difficult. The Alcubierre drive remains a beautiful piece of speculative engineering, a reminder that the universe's rulebook is complex and may still contain chapters we have only begun to read. A warp drive may bend the rules of space, but it does not solve the silence. If the universe is so vast and ancient, teeming with potential, why have we never seen a single sign of another civilization? This profound question, posed by physicist Enrico Fermi, is the heart of the Fermi paradox. The cosmos should be buzzing with activity, yet we hear only a deafening quiet. Among the many proposed solutions, one stands out for its elegant and unsettling simplicity. It is called the zoo hypothesis. This idea suggests we are not alone, we are merely quarantined. Advanced civilizations know we are here, but they have chosen to place Earth under a form of cosmic observation, a galactic wildlife preserve where a young, developing species is left to evolve without interference. In this view, our solar system sits inside a kind of interstellar nature reserve, with rules of non-interaction as strict as those in a terrestrial national park. The more advanced galactic community watches from a distance, perhaps through undetectable monitoring probes, ensuring we do not harm ourselves or the ecosystem, but refusing to make contact until we reach a certain level of maturity, perhaps technological or ethical. The Great Silence, then, is not a sign of emptiness but of a deliberate policy. It is the hush of a museum, not a tomb. This hypothesis resolves the paradox by turning our loneliness into a stage of development. It explains why we see no megastructures like Dyson spheres blotting out stars, and why our radio signals seem to vanish into a void without reply. A truly advanced culture would have technology so far beyond our comprehension that remaining hidden from our primitive senses would be trivial. They could be all around us in dimensions or frequencies we cannot perceive, and we would never know. The zoo hypothesis asks us to consider a humbling possibility. Our frantic efforts to search for extraterrestrial intelligence might be akin to ants in a carefully tended garden, building tiny towers and signaling with pheromones, completely unaware of the gardeners who watch with detached curiosity, waiting to see what the colony will become. Our entire history, with all its wars, art, and discovery, could be a fascinating documentary for unseen audiences. The question then shifts from where are they to what are they waiting for? What milestone must humanity reach before the keepers of the zoo decide we are ready to join the conversation? The quiet observation of a cosmic zoo offers one peaceful answer to our solitude, but the truth may be far more terrifying. The Great Filter presents a universe not of careful gardeners but of silent graveyards. This solution to the Fermi paradox is stark and statistical. It suggests that somewhere between the emergence of life on a planet and its evolution into a galaxy-spanning civilization, there exists a barrier so lethal, so nearly impossible to overcome, that it filters out almost every aspiring species. This is the Great Filter, a cosmic bottleneck of extinction. The haunting question is not if it exists, but where. Is this filter safely behind us in the distant past, or does it loom ominously in our future? If the filter is behind us, we are cosmic lottery winners. It means one of the steps that led to us is astonishingly rare. Perhaps the leap from non-living chemistry to the first self-replicating life, abiogenesis, is a fluke of such staggering improbability that it has only happened a handful of times in the entire galaxy. Or maybe the evolution of complex eukaryotic cells, which took over 2 billion years on Earth, is the true bottleneck. If this is the case, the silence is a sign of a young, empty galaxy where we are among the first, or the only, to have made it this far. It means we have already passed the hardest test, and the stars could be ours for the taking. But the alternative is a chilling prospect. What if the Great Filter lies ahead? This is the more disturbing interpretation of our loneliness. It proposes that the step from a technological civilization like ours to an interstellar one is the wall that shatters everyone. Perhaps every intelligent species eventually creates the technology for its own annihilation, whether through nuclear war, engineered pandemics, or runaway artificial intelligence. Or maybe the filter is an external cosmic catastrophe we have yet to encounter, like a gamma-ray burst that sterilizes planets on a galactic schedule, or the inevitable discovery of a destabilizing physics that destroys any civilization foolish enough to unlock it. In this view, the eerie silence is a warning. Every civilization that ever broadcast a signal, that ever looked up at the stars with hope, has already been silenced. We are not hearing from them because they are all dead. Our continued existence, then, is not a sign of success but of naivete. We are simply not yet advanced enough to have reached the cliff's edge that everyone else has fallen over. The evidence we see is deeply ambiguous. On one hand, our planet has remained undisturbed for billions of years, with no signs of visitation or colonization, which could suggest no one has ever made it to the other side of the filter. On the other hand, our own rapid technological ascent and the looming threats we have created for ourselves suggest the filter-ahead scenario is all too plausible. The Great Filter transforms the search for extraterrestrial life into a race against time, not to find company, but to discover our own fate before it is too late. The Great Filter suggests a universe of silent graveyards, but there is an explanation for the quiet that is far more active and far more sinister. This is the dark forest theory, a chilling answer to the Fermi paradox that frames the cosmos not as a dead or quarantined place, but as a state of perpetual hidden war. The metaphor comes from science fiction, but the logic is coldly rational. Imagine an ancient pitch-black forest on a moonless night. In this forest, you are a hunter, but you are also prey. You cannot see the other hunters, but you know they are there, hidden among the trees. The first rule of survival in this dark forest is absolute silence. To make a sound, to light a fire, is to reveal your position, and any other hunter who hears you cannot afford to assume you are friendly. The safest, indeed the only rational, course of action is to immediately fire a shot in the direction of the noise. Annihilation is the only guarantee of safety. Now translate this to the cosmic scale. Every civilization is a hunter in the dark forest of the universe. The distances are so vast, communication so slow, and the technological differences so potentially immense that trust is impossible. A civilization just a few centuries more advanced than ours could possess weapons of unimaginable power, perhaps the ability to destabilize a star or redirect asteroids with relativistic speed. From their perspective, a newly noisy species like humanity, broadcasting radio and television signals into the void, is not a potential friend. We are a potential threat, a spark in the tinderbox. The most logical, cost-effective response for any advanced civilization that detects our signals is not to say hello. It is to send a relativistic kill vehicle, a projectile accelerated to a significant fraction of light speed, to sterilize our solar system before we can ever become a danger to them. This is not a theory of malevolence, but one of supreme cosmic pragmatism. It explains the silence perfectly. Any civilization that survives long enough to become interstellar has learned the first rule. Do not broadcast your location. They are all hiding, listening intently, and ready to strike at the first sign of another. Our efforts with projects like SETI, the search for extraterrestrial intelligence, then take on a terrifying new character. We are not just listening for a greeting, we are shining a spotlight into the dark forest and shouting, "We are here." In this view, the lack of visible megastructures is not because civilizations die out, but because they deliberately cloak their energy signatures. The universe appears barren because every intelligent species that has survived has become expertly camouflaged, a silent predator in an endless night. The dark forest offers no hope of galactic community, only a permanent, silent standoff where the only safe civilization is an invisible one. It suggests that the ultimate destiny of intelligence is not to explore the stars together, but to vanish into the shadows, forever afraid of the light. Perhaps the simplest answer to the silence is also the most profound. After all the theories of hidden predators and cosmic filters, we must confront a possibility that feels both lonely and deeply significant. What if we are, for all practical purposes, alone? This is not a statement about the entire universe, which is likely infinite, but about our own galactic neighborhood and the reachable cosmos. The rare Earth hypothesis builds a compelling case that the conditions for complex, intelligent life are not just a matter of finding a planet in the habitable zone. It is a cascade of improbable accidents, a cosmic checklist so demanding that Earth may be a 1 in a trillion fluke. Consider the prerequisites. You need a stable, long-lived star, not too big and not too small. Our Sun is a G-type main sequence star, a common but not overwhelmingly so class. You need a rocky planet at just the right distance, with plate tectonics to recycle carbon and regulate climate. You need a large moon like ours to stabilize the planet's axial tilt, preventing chaotic climate swings that would snuff out evolution. You need a magnetic field generated by a molten iron core to shield the surface from lethal cosmic and solar radiation. You need a gas giant like Jupiter in the outer system to act as a gravitational shield, deflecting a constant barrage of comets and asteroids that would otherwise cause constant mass extinctions. The list goes on, from the precise timing of catastrophic asteroid impacts that spurred evolution without wiping it out, to the unlikely jump from simple prokaryotic cells to complex eukaryotic life, which took over 2 billion years on our planet. Each step is a bottleneck, a cosmic lottery draw where the odds are stacked against the emergence of a species that can look up and wonder. When you multiply all these probabilities together, the number of advanced civilizations in a galaxy like ours could easily be 1 or even 0. We might not be hearing from anyone because there is simply no one else here to call. This idea transforms the Fermi paradox from a puzzle into a statement of fact. The silence is not a mystery to be solved. It is the expected background noise of a universe where intelligence is a fleeting, precious spark. It means that every star you see at night, every swirling nebula, is likely a beautiful, empty cathedral. There are no ancient empires, no cosmic wars, no galactic federations. There is only us and the quiet, indifferent stars. This perspective carries a staggering weight of responsibility. If we are the first or among the very first to reach this stage in our galaxy, then the future of consciousness, of meaning, and of cosmic legacy may rest entirely in our hands. We are not just a young species, we might be the pioneers. Our choices, our survival, our expansion into the galaxy could set the template for all life that may follow in the billions of years to come. The universe has been waiting in silence for a voice. That voice for now might only be ours. The profound silence of the cosmos might not mean we are alone or doomed. It could signal a universal graduation. When a civilization reaches a certain technological zenith, its greatest achievement may be to leave the physical world behind entirely. This is the transcendence hypothesis, a solution to the Fermi paradox that suggests advanced beings do not die out. They simply evolve into a state we cannot perceive. Picture an ant colony, industrious and complex, building its mounds and communicating with intricate pheromone trails. From the perspective of an ant, its world is vast and complete. Yet, just inches above the colony, humans are engaged in a frenzy of invisible activity, sending streams of data through the air, having video calls across continents, and accessing the collective knowledge of our species through a digital web. The ants are utterly oblivious to this vast, layered reality existing in the same space. To them, the air is empty. We are not hiding from the ants. We are simply operating on a plane of existence they lack the senses or concepts to detect. The same could be true for cosmic civilizations. The endpoint of technological progress might not be interstellar empires, but a transition into a post-biological state. A species could upload its collective consciousness into a planetary-scale quantum computer, or engineer itself into pure energy, existing as patterns of information woven into the fabric of spacetime itself. Their entire civilization might reside in simulated realities of their own making, universes far richer and more controllable than the harsh, limiting physics of the outer cosmos. Or they might learn to access higher spatial dimensions, moving into realms we are geometrically incapable of seeing, like flatlanders unable to comprehend a sphere passing through their two-dimensional plane. In such a state, why would they build visible Dyson spheres or broadcast primitive radio waves? Their communication and energy needs would be met through means we cannot fathom, using quantum entanglement or dimensional vibrations that leave no trace in our electromagnetic spectrum. They would be all around us, a hidden ecology of mind, as indifferent to our chemical rockets and radio telescopes as we are to the chemical signals of bark beetles. The great silence, then, is not silence at all. It is a cacophony of conversations happening on frequencies we are deaf to, in dimensions we are blind to. Our search for alien life has been like scanning the ocean's surface with a net, looking for birds, while an entire universe of intelligent whales sings complex songs in the dark depths below. We are listening for a whisper in a language that was abandoned eons ago. This idea reframes our place in the universe not as a potential member of a galactic club, but as a toddler still learning to crawl in a nursery, while the adults have long since moved on to forms of existence we cannot yet dream of. The profound silence left by transcendent civilizations hints at a universe where information is the ultimate currency. But what happens when the universe's most efficient shredder, a black hole, seems to destroy that currency forever? This is the black hole information paradox, a conflict that has torn at the very foundations of physics for decades, pitting Einstein's theory of general relativity against the quantum laws that govern the subatomic world. At its heart is a simple, devastating question. When something falls into a black hole, is all information about that object, what it was made of, its shape, its history, truly and irrevocably lost? General relativity, our theory of gravity, says yes. The mathematics describing a black hole are remarkably simple. They tell us a black hole can be completely described by just three things: its mass, its electric charge, and its spin. If you throw a grand piano, 1,000 encyclopedias, or a living creature into a black hole from the outside, the result is identical. The black hole simply gets a little more massive, spins a little differently, but all the intricate details of what fell in are erased, crushed into the singularity. This violates a sacred principle of quantum mechanics, the law of unitarity, which states that information can never be destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. If quantum information is lost in a black hole, then the predictability that underpins all of physics breaks down. The universe would become fundamentally random and unpredictable. Stephen Hawking identified this crisis in the 1970s. He showed that black holes are not completely black. Due to weird quantum effects at the event horizon, they slowly evaporate, emitting a faint glow we now call Hawking radiation. This radiation, however, is purely thermal, like the heat from a stove. It carries no information about what fell in, so when a black hole finally evaporates completely, all it leaves behind is this bland, featureless heat. The information about the grand piano and the encyclopedias is gone forever. Hawking famously bet other physicists that information was lost, declaring black holes the ultimate cosmic shredders. The physics community was thrown into chaos. If Hawking was right, we would need to rewrite the textbooks. The conflict escalated with an even more alarming proposal, the firewall paradox. If information must escape a black hole via Hawking radiation, then the event horizon, the point of no return, might not be the smooth gateway described by Einstein. Instead, it could be a searing wall of high-energy particles, an inferno that would incinerate anything trying to cross. An astronaut falling in would not experience the gentle stretching of spacetime. They would be vaporized instantly. This firewall would protect information from being lost, but it would mean our understanding of gravity is profoundly wrong at the horizon. The solution, emerging from decades of fierce debate, points back to the holographic principle we explored earlier. The information swallowed by a black hole is not stored in its inaccessible interior. It is encoded on its two-dimensional surface, the event horizon. Hawking radiation is not random noise escaping from the void. It is the slow, careful readout of that encoded information. Imagine the black hole as a giant, chaotic hard drive. When something falls in, its information is not deleted, but written onto the drive in an incredibly scrambled, encrypted form. The Hawking radiation is like the heat and hum of that hard drive working. As the black hole evaporates, it is slowly decrypting and emitting that information, bit by bit, in the radiation. The process is so complex and scrambled that to an outside observer, it looks like random heat, but the information is, in principle, preserved. Recent breakthroughs, particularly in understanding the geometry of spacetime using quantum entanglement, suggest that black holes are the ultimate quantum computers, performing the most complex information processing in nature. The interior of the black hole and the Hawking radiation outside are entangled, a quantum link that ensures no information is ever lost, even if we cannot easily decode it. Hawking himself eventually conceded the bet, agreeing that information probably does escape. This paradox has forced us to see spacetime not as a fundamental stage, but as an emergent structure built from quantum information and entanglement. The resolution hints that in the clash between gravity and quantum mechanics, information always wins. Black holes may be the universe's ultimate quantum hard drives, but what is the actual wire connecting them? The answer could be hiding in plain sight, woven into the most common yet bizarre phenomenon in all of physics, quantum entanglement. Two particles become entangled, and no matter how far apart they fly, measuring one instantly determines the state of the other. This spooky action at a distance, as Einstein called it, seems to violate the cosmic speed limit of light, transmitting information faster than any signal could travel. For decades, this was seen as a profound mystery of the quantum world, separate from the grand curvature of spacetime described by gravity. But a revolutionary idea, known by the deceptively simple equation ER equals EPR, proposes these are not two different puzzles. They are the same picture. This conjecture suggests that every pair of entangled particles is not communicating through some invisible field. They are literally connected by a microscopic wormhole. The EPR part refers to a famous 1935 paper by Einstein, Podolsky, and Rosen that first highlighted the weirdness of entanglement. The ER stands for Einstein and Rosen, who in the same year published a paper on bridges in spacetime, later known as Einstein-Rosen bridges or wormholes. The conjecture boldly claims these two ideas, conceived in the same year by the same physicist to solve different problems, are actually describing the same underlying reality. An entangled pair of electrons, for instance, would not be two separate objects with a mysterious link. They would be two mouths of a single, incredibly tiny wormhole, a shortcut through the geometry of spacetime itself. This wormhole would be non-traversable, meaning you could not send a spaceship or even a radio signal through it, but its existence would physically embody the quantum connection. This idea turns our understanding of space inside out. It suggests that the fabric of spacetime, the stage upon which everything plays out, is not fundamental. It is an emergent structure knitted together from a vast cosmic web of quantum entanglement. Think of a three-dimensional tapestry. From a distance, it looks like a smooth, continuous image. But up close, you see it is made of countless individual threads woven together. In this analogy, the threads are the entangled connections between particles, and the smooth image of space is the emergent pattern they create. Where entanglement is dense and complex, space itself crystallizes. Where there is no entanglement, space ceases to exist. This provides a breathtaking bridge between quantum mechanics and gravity, the two great pillars of modern physics that have stubbornly refused to unite. Gravity, in this view, is not a fundamental force, but a side effect of the universe trying to maintain these quantum connections. When you entangle more and more particles, the space-time geometry that emerges naturally curves, producing the effects we call gravity. The implications are staggering. It could mean that the Big Bang was not an explosion in a pre-existing void, but the moment when a vast network of quantum connections first froze into the geometry we call spacetime. It suggests that black holes where spacetime curvature becomes infinite are regions where entanglement is being stretched to its absolute limit or perhaps severed. The wormhole link between entangled particles offers a geometric picture for how information might escape a black hole, not by traveling out, but by being teleported through these quantum bridges. While still a theoretical framework, ER equals EPR is more than just a clever idea. It is a new language for describing reality, one where the weirdest features of the tiny quantum world are directly responsible for the shape of the cosmos. It tells us that the universe is not just connected, it is literally stitched together, with every entangled particle holding a single thread in the fabric of everything. But if wormholes stitch reality together, could they also stitch time into a perfect, unbreakable loop? The Novikov self-consistency principle offers a radical answer, one that turns the chaos of time travel into a story with a single, inevitable ending. Proposed by Russian physicist Igor Novikov in the 1980s, this principle is a law of cosmic plot armor. It states that if time travel to the past is possible, then the timeline is protected from paradoxes by its own geometry. Any action a time traveler takes in the past was always a part of that past. You cannot change history because you already did what you always did. The universe, in this view, is a single, immutable narrative loop. Think of a vinyl record. The groove is a physical spiral containing the entire song. The needle tracing that groove is like the flow of time. Now imagine the needle could somehow jump back to an earlier part of the groove. The Novikov principle says that when it jumps, it will not carve a new, divergent path. Instead, the groove itself will subtly warp to guide the needle, ensuring it plays the exact same notes that led to the jump in the first place. The timeline is fixed not by fate but by the consistent laws of physics themselves. Let's make this concrete with the classic grandfather paradox. You build a time machine, go back, and intend to prevent your grandfather from meeting your grandmother. According to Novikov, the universe conspires to stop you. Your gun jams, you get lost on the way. A sudden downpour cancels the crucial event. Or, in a darker twist, you succeed in pulling the trigger, but the man you shoot turns out not to be your biological grandfather after all. Perhaps your grandmother was already pregnant by someone else, and the man you thought was your grandfather raised the child as his own. Your violent act does not erase your existence, it ensures it by setting in motion the precise chain of events that leads to your own birth and your eventual decision to take that trip. You are always part of the story. This is not about luck or coincidence, it is about physics enforcing consistency. The principle suggests that the probability of events that would create a paradox is exactly zero. The laws of nature simply do not allow inconsistent states to exist. If you are in the past, then your presence and your actions are already factored into the history that produced you. You are not an outside editor, you are a character who was always there, your lines already written into the script. This creates a strange, deterministic beauty. Every time travel story becomes a closed loop, a perfect circle with no loose ends. The famous bootstrap paradox, where an object or piece of information has no origin, fits perfectly here. Imagine a composer travels back in time and gives a young Beethoven a symphony he claims is Beethoven's own future work. Beethoven copies it and publishes it, becoming famous for it. The symphony is never actually composed by anyone, it just eternally exists, passed from the future to the past. In Novikov's universe, this is not a paradox, it is just how that piece of music always came to be. Its origin is the loop itself. While this solves the headache of paradoxes, it imposes a profound constraint on free will. If you travel to the past, you are not free to act differently than you already did. Your journey and every action you take there are predetermined, locked into the timeline's single, self-consistent shape. It suggests a universe without alternate histories or branching paths, only one intricate, interlocked story where every effect loops back to become its own cause. The Novikov principle transforms time from a river you can divert into a Möbius strip, a single surface where past and future are forever linked, writing and rewriting each other in an endless, immutable dance. The rigid consistency of Novikov's timeline feels almost claustrophobic, a universe with no room for chance. But what if probability itself is an illusion born from countless worlds constantly pushing and pulling on each other? The many interacting worlds interpretation offers a breathtakingly physical alternative to the silent branching of Everett's many worlds. In this radical variant of quantum theory, parallel realities are not just abstract mathematical branches, they are concrete, physical worlds that exist alongside our own, separated by a tiny gap, and they are constantly in contact. These worlds are not splitting, they were always there, an infinite stack of nearly identical universes, each differing by the tiniest quantum detail. In every single one of these worlds, every particle has a definite position and velocity, obeying the classical laws of Newton. There is no blurry superposition, no wave function collapse. So what creates the bizarre quantum behavior we observe? The answer is a force, a literal, physical repulsion between these neighboring worlds. Imagine an infinite crowd of nearly identical dancers, all performing the same routine on an infinite stage, but each dancer is slightly out of step with the ones next to them. Now, imagine each dancer feels a gentle but firm push, a desire to stay different from their immediate neighbors. This mutual repulsion is the engine of quantum mechanics. In a classic experiment like the double slit, a particle is fired at the barrier. In our world, it goes through one slit, but in the world next to ours, an identical particle goes through the other slit. The repulsive force between these two worlds causes their paths to bend, creating an interference pattern on the detector screen. The particle in our world is literally being nudged by the ghostly presence of its neighbors in other worlds. We do not see a single particle acting like a wave. We see a single particle being pushed around by an invisible crowd of its other selves. This interaction explains probability without any need for randomness. The chance of finding a particle in a particular location is not a fundamental law. It is simply a measure of the density of worlds. If 90% of all the parallel worlds have a particle in a certain spot, then the probability of finding it there in any given world like ours is 90%. The repulsive force ensures the worlds spread out according to these odds. It is a stunningly mechanical picture of reality. There is no mystery, no collapse, just an infinite ensemble of classical universes all shoving each other around. This interpretation makes quantum theory feel less like magic and more like a cosmic crowd dynamic. It even suggests a potential, though unimaginably difficult, way to test it. If worlds interact, there might be an incredibly faint residual force, a whisper of a push from a neighboring reality that could leave a minuscule signature in extremely sensitive experiments. While firmly in the realm of foundational theory, the many interacting worlds idea re-enchants the multiverse, not as a silent library of possibilities, but as a bustling, jostling metropolis of realities, each one solid and real, forever feeling the gentle pressure of the infinite others just a quantum hair's breadth away. The bustling metropolis of parallel worlds offers a strange kind of comfort, a promise that every possibility is realized somewhere. But what if this branching reality holds a far more personal and deeply unsettling implication for your own existence? The thought experiment of quantum immortality pushes the many worlds interpretation to its most intimate and disturbing limit. It suggests that from your own subjective point of view, you can never truly experience death. Your conscious awareness will always find itself in a branch of reality where you survive, no matter how unlikely that survival may seem. This is not a claim about magic or destiny, but a chilling logical consequence of an infinite branching multiverse. Consider a classic, if grim, scenario. You are the subject in a modified version of Schrödinger's famous experiment. Instead of a cat, you are placed in a box with a device that, at a random quantum trigger, will either release a harmless puff of air or a lethal dose of poison. According to the Copenhagen interpretation, when the box is opened, the wave function collapses and you are either alive or dead. In the many worlds view, however, the universe splits at the moment of the quantum trigger. In one branch, the device fires the poison and you die instantly. In the other, it releases the air and you live. Both outcomes are equally real. Now ask yourself a simple question. In which branch does your conscious experience continue? From the inside, you can only be aware of the outcome where you are alive to have an experience. The version of you that dies has no point of view left, so from your first-person perspective, you will always find yourself stepping out of the box, bewildered but breathing. No matter how many times you repeat the experiment, your subjective timeline will be the one where you miraculously survive every single time. The experimenter outside the box sees a different story. They will see you die in roughly half of the trials, but you, the subject, will never witness your own death. You will only experience the unlikely chain of universes where the quantum dice roll in your favor. Now scale this up from a laboratory box to the chaotic dangers of everyday life. Every moment presents countless quantum possibilities. When you cross a street, there are branches where a driver is distracted and swerves, branches where you trip, and branches where you cross safely. The quantum immortality argument suggests your consciousness is like a train that only rides tracks leading away from fatal derailments. You might have a close call, a brush with disaster that leaves you shaken, but you will always find yourself in the reality where the car missed you by an inch, not the one where it did not. This leads to bizarre and paradoxical conclusions. Imagine an elderly person on their deathbed. In the vast majority of branching futures, they peacefully pass away. But there will always exist an increasingly vanishingly small set of branches where a quantum fluctuation, however improbable, prevents death at the very last instant. A random neuron fires in just the right way. A sudden, unexplained remission occurs. If consciousness follows survival, then the subjective experience of that person could, in principle, continue indefinitely, leaping from one increasingly improbable branch to the next. They would find themselves in a reality where medical science cannot explain their recovery, a reality that becomes stranger and more isolated as the branches where friends and family exist grow ever more distant. The world would seem to bend around their continued existence in increasingly surreal ways. This is, of course, a thought experiment, not a proposal for how reality works. Most physicists and philosophers reject it as a misinterpretation, arguing that consciousness is likely tied to a specific brain state and cannot hop between branches. When your brain ceases to function in a branch, that particular stream of awareness ends. There is no you to jump to the next branch, yet the experiment's power lies in its stark confrontation with the nature of self and observation. It forces us to ask what we truly mean by I. If the multiverse is real, which copy of you is the real you? The answer might be all of them, each with its own uninterrupted stream of consciousness. From the outside, your life appears as a tree with many dead ends. But from the inside, you only ever walk the one seemingly charmed path that never reaches a true terminus. It presents a universe where, for every conscious being, death is something that only ever happens to other versions of themselves, a statistic observed from the outside but never, ever felt from within. The unsettling possibility that your consciousness might always sidestep death in some quantum branch forces us to confront a far more tangible mystery, one etched across the entire sky. This is the cosmic microwave background, the oldest light in the universe, a nearly uniform glow from when the cosmos was just 380,000 years old. It is our most pristine snapshot of the infant universe, and according to our best theories, it should be almost perfectly smooth with only tiny, random fluctuations. But when scientists created exquisitely detailed maps of this ancient light, they found something deeply strange. The universe appears to have a preferred direction, a cosmic alignment so improbable it was nicknamed the axis of evil. The temperature fluctuations in the CMB are not completely random. They show a curious alignment along a specific axis in space, as if the early universe was somehow lopsided or spinning on a preferred axis. This violates a cornerstone of modern cosmology, the cosmological principle, which states that the universe is homogeneous and isotropic, meaning it looks the same in all directions and has no special center. The axis of evil suggests that on the largest scales, the universe might have a handedness, a fundamental asymmetry written into its first breath. Even stranger is the famous cold spot, a vast region of space in the constellation Eridanus that is significantly colder than the surrounding CMB. It is so large and so cold that its probability of occurring from random chance is less than 2%. It looks like a cosmic bruise, a place where the ancient universe was missing a colossal amount of energy. Standard explanations like a giant supervoid, a region with far fewer galaxies, have been proposed, but even the largest known voids do not seem sufficient to explain the profound chill. These anomalies are more than just statistical glitches. They are cracks in the foundation of our standard model of cosmology, and some theorists believe they are not flaws but fingerprints. Fingerprints of what existed before our Big Bang. One radical interpretation is that the axis of evil is a relic of a previous cosmic phase. If our universe was born from a cyclical event, like a big bounce or an ekpyrotic collision, the spin or geometry of that prior cosmos could have imprinted a directionality onto our own, a kind of cosmic inheritance that breaks perfect symmetry. The cold spot could be even more dramatic evidence of a larger reality. In the bubble universe model of eternal inflation, our cosmos is one bubble in a frothing multiverse. If, during its early expansion, our bubble universe collided or even gently brushed against a neighboring bubble, the energy of that collision would have left a distinct circular imprint on the CMB. The cold spot, with its sharp edges and unusual profile, is a prime candidate for such a scar, a cosmic kiss from another reality that forever altered the temperature of our sky. These ideas transform the CMB from a simple baby picture into a potential palimpsest, a canvas where the shadows of other universes or previous cosmic cycles might still be visible. They suggest that the ultimate origin of everything might not be a singular, solitary event, but part of a vast, interactive, and perhaps eternal tapestry of creation, where the echoes of other worlds are frozen in the first light we can see. The ancient light from distant galaxies carries a hidden message in its color, a shift toward the red end of the spectrum. For a century, this redshift has been the cornerstone of our cosmic story, interpreted as a Doppler effect from galaxies rushing away in an expanding universe. But what if we have been reading the message wrong? A persistent challenger, the tired light hypothesis, offers a radically different translation. It proposes that light, on its epic journey across billions of light years, simply grows tired. It loses energy not because space itself is stretching, but through some interaction with the fabric of the cosmos, causing its wavelength to lengthen and shift to red. In this view, the universe might be static, eternal, and not expanding at all. the idea is elegantly simple, a direct challenge to the need for a Big Bang. Instead of galaxies flying apart on an inflating spacetime grid, they could be held in a roughly steady state. The redshift we see is not a measure of velocity, but a record of the journey's toll. Early proponents suggested that light might lose energy by bumping into interstellar dust or gas, but that would scatter the light and blur distant objects which we do not observe. Modern versions propose more subtle mechanisms, like a tiny interaction between photons and other quantum particles in the vacuum of space, a gradual energy drain over cosmic distances. This would mean a distant galaxy is not actually moving away at tremendous speed. It just looks that way because its light arrives exhausted. The appeal of tired light is philosophical as much as scientific. It restores a kind of classical permanence to the cosmos, a universe without a definite beginning or an inevitable end. Yet, for all its elegance, the hypothesis has consistently failed where the expanding universe model has triumphed. One crucial test is time dilation. In an expanding universe, the stretching of space affects not just light waves but time itself. We should see the clocks of distant, fast-receding galaxies running slow. And we do. Observations of the light curves of distant supernovas show they evolve more slowly than nearby ones, exactly as the expansion model predicts. A simple tired light mechanism where photons just lose energy would not produce this slowing of time. The light would be redder, but the supernova explosion would appear to unfold at the same rate as a local one. The data clearly shows it does not. Another definitive strike comes from the cosmic microwave background. The expanding universe model predicts this afterglow with near-perfect precision, a natural consequence of a hot, dense beginning. A static, tired light universe has no natural explanation for this uniform, thermal radiation bathing all of space. To account for it, proponents must graft on additional, ad hoc assumptions, like a universe filled with a thermalizing fog of ancient starlight, a contrivance that lacks the explanatory power and elegance of the Big Bang. Furthermore, the detailed pattern of temperature variations in the CMB, the very seeds of galaxy formation, matches the predictions of an expanding, evolving cosmos with stunning accuracy. The tired light model struggles to reproduce these intricate details without invoking the very expansion it seeks to replace. While the scientific consensus firmly favors the expanding universe, the tired light hypothesis endures as a vital intellectual foil. Its repeated failures have, ironically, strengthened the standard model by forcing it to make precise, testable predictions that have been spectacularly confirmed. It reminds us that even our most fundamental assumptions must be relentlessly questioned. The redshift of starlight is an observation. The expanding universe is our best explanation for it, but the story is written not just in the color of the light, but in the slowed tick of cosmic clocks and the whisper of ancient heat that fills the void. Gravity has reigned as the universe's sole architect for centuries, sculpting galaxies and guiding planets in a silent, relentless dance. But a small yet vocal group of thinkers proposes we have been worshipping the wrong force entirely. The electric universe theory is a radical, controversial cosmology that dethrones gravity and places electromagnetism on the cosmic throne. In this view, the cosmos is not a near-empty vacuum dotted with isolated islands of matter. It is a vibrant, dynamic sea of electrically charged plasma, and its currents and magnetic fields are the true sculptors of everything we see. The theory begins with a fundamental reinterpretation of stars, including our Sun. Mainstream astrophysics sees the Sun as a giant nuclear fusion reactor, its heat and light generated by crushing hydrogen into helium at its core. The electric universe model paints a very different picture. It proposes the Sun is an electric discharge node in a galactic circuit. Instead of generating its own power internally, it acts more like a giant, luminous anode, receiving electrical energy from the vast plasma currents that flow through the Milky Way. The sunspots, solar flares, and coronal loops we observe are not just magnetic phenomena. They are the direct signatures of this cosmic power flow, arcing and sparking across its surface. This electrical input, proponents argue, better explains the Sun's mysteriously hot corona and the acceleration of the solar wind. This electrical thinking extends to the very birth of solar systems. Standard theory says stars and planets condense from collapsing clouds of gas and dust under gravity. The electric universe suggests a far more dramatic genesis. It envisions a cosmic-scale version of a phenomenon you can see in a lab, a plasma Z-pinch. When powerful electromagnetic currents flow through plasma, they can pinch and twist it into concentrated knots, spinning disks and filamentary structures. In the depths of space, these electromagnetic pinches could forge stars and align planets into orbits not through gentle collapse, but through violent, sculpting currents. The spiral arms of galaxies are not density waves of stars, but colossal Birkeland currents, twisting rivers of electricity flowing through intergalactic space, lighting up the stars within them like beads on a wire. This perspective seeks to explain cosmic mysteries without invoking dark matter or black holes. The rotational speeds of galaxies that defy gravitational predictions are attributed not to invisible halos of dark matter, but to the powerful magnetic fields generated by these galactic-scale currents. Even the bizarre shapes of some nebulae and the precise alignment of celestial bodies are seen as scars and structures carved by ancient electromagnetic forces. For its advocates, this is a more unified and testable vision of the cosmos, one rooted in the behavior of plasma we can observe in laboratories and in near-Earth space. Yet, the electric universe theory exists in a state of profound rejection by the mainstream scientific community. Critics point to its lack of mathematical rigor, its failure to make precise, quantitative predictions that match astronomical data, and its tendency to offer alternative explanations for phenomena that are already well understood within the standard gravitational and nuclear models. The theory often relies on qualitative analogies rather than the precise equations that allow cosmologists to predict the cosmic microwave background or the life cycle of stars. Furthermore, it dismisses overwhelming evidence from the neutrino flux of the Sun confirming nuclear fusion to the gravitational wave signatures of merging black holes. To most scientists, it is not a competing theory, but a collection of misconceptions that ignores the successful, predictive power of established physics. The chasm between the two views is not merely academic, it is a clash of fundamental methodologies. The electric universe stands as a stark reminder that our cosmic story is built on consensus, but that consensus must forever withstand the challenge of radical reimagining. It asks whether we have become too comfortable with an invisible, dominating force like gravity, while ignoring the crackling, visible power of the electric forces that light up our own sky. Our own moon, that familiar silver disk in the night sky, holds secrets that challenge its very origin. The hollow moon hypothesis is not a fringe idea from science fiction, but a conspiracy theory with roots in genuine, perplexing scientific data. It proposes that Earth's companion is not a natural celestial body, but an artificial construct, perhaps a hollowed-out spaceship, a colossal observation post, or even a relic from a forgotten cosmic war. The theory begins with a sound, or rather, the echo of one. During the Apollo missions, astronauts deliberately crashed the lunar modules and spent rocket stages into the moon's surface to create artificial moonquakes for scientific study. The results were utterly baffling. The moon rang like a bell. Seismic sensors recorded vibrations that lasted for astonishingly long periods, sometimes over an hour. On Earth, a quake of similar magnitude would shudder and settle in minutes. This prolonged reverberation suggested a structure that was far less dense at its core, or perhaps even hollow. Proponents point to this as direct evidence of a vast, empty interior space beneath a manufactured crust. Adding to the mystery is the moon's bizarre density and composition. It is far less dense than Earth, and while its surface is rich in materials like titanium and chromium, elements common in spacecraft hulls, its overall makeup is strangely unbalanced. Some analyses suggest the Moon's crust is much harder and more resilient than it should be for a body of its size, as if engineered to withstand impacts. The most famous anomaly, however, is its precise celestial choreography. The Moon is exactly the right size and distance to perfectly eclipse the Sun from our perspective, a statistical oddity that some argue is too perfect to be natural. Could it be positioned intentionally? Ancient astronaut theorists weave this into a grander narrative, connecting the hollow Moon to humanity's own myths and megalithic structures. They ask why so many ancient cultures, from the Sumerians to indigenous tribes, speak of a time before the Moon existed in the sky. They highlight enigmatic structures that seem aligned with lunar cycles in ways that would require advanced astronomical knowledge. The hypothesis suggests the Moon was placed in orbit by an advanced civilization, either to stabilize Earth's tilt for their own purposes, to monitor the development of life, or as a generation ship that brought our earliest ancestors here. This transforms the Moon from a dead rock into a silent sentinel, its craters not just scars from random impacts, but perhaps the remnants of ancient machinery or entry points to a labyrinthine interior. While mainstream science offers explanations for the moonquake data, such as a dry, fractured interior that vibrates differently than Earth's watery crust, and attributes the eclipse to a temporary cosmic coincidence that will change over time, the anomalies persist in the public imagination. The hollow Moon hypothesis forces a profound question about our closest neighbor. Is it a testament to the random beauty of cosmic formation? Or is it the oldest and largest artifact in human history, hanging in plain sight, watching us, waiting for the day we uncover its true purpose? The Moon's silent watch over Earth may be a recent arrangement in a far more dramatic cosmic history. Ancient myths from cultures across the globe speak of a lost golden age, a time when the sky looked profoundly different, dominated by a great stationary light that was not our sun. A radical branch of the electric universe cosmology offers a staggering explanation for these universal stories. It is called the Saturnian polar configuration, and it proposes that within human memory, the planets we know today were arranged in a celestial column, with a brown dwarf Saturn acting as a second, benevolent sun for our prehistoric ancestors. In this model, several thousand years ago, Earth was not an isolated planet orbiting the Sun as it does now. It was gravitationally captured in a polar alignment with other bodies, possibly Venus, Mars, and a shrouded Saturn. This configuration would have placed Saturn, glowing not from nuclear fusion but from intense electrical activity, directly above Earth's North Pole. From the perspective of every human on the planet, this colossal, radiant orb would have hung motionless in the sky, a permanent, gentle fixture that never rose or set. This, theorists argue, is the true source of the nearly universal myth of a primordial paradise, a time of perpetual dawn or twilight under a fixed heavenly light, often described as a pillar or a world mountain. The Golden Age was not a metaphor but a literal description of the sky. The light from an electrically active Saturn would have been softer and more diffused than our Sun's, possibly tinted golden or reddish, bathing the Earth in a perpetual, tranquil glow that allowed for a mild, global climate without seasons or violent storms. This stable, luminous anchor in the heavens became the central god of ancient pantheons, the unwavering father figure around which all myth and ritual revolved. Then, according to the theory, came the cataclysm. The delicate electromagnetic balance of this polar configuration destabilized. A massive electrical discharge, a cosmic short circuit on a solar system scale, erupted between the bodies. This was the Great War in heaven described in countless mythologies. The planets were violently scattered into their current orbits. In this event, Saturn's sheath was stripped away, revealing the gas giant we see today, while Earth was subjected to apocalyptic electrical scarring, massive flooding, and a sudden, terrifying tilt of its axis. The great pillar in the sky broke apart, the golden age ended in fire and flood, and the familiar, wandering planets were born from the debris of this celestial disintegration. Proponents point to the startling consistency of ancient symbols as evidence. The ubiquitous image of the sun cross, a circle with a cross inside, is reinterpreted not as our sun, but as the polar view of Saturn with its luminous plasma rings seen face-on, a stationary cross in the sky. Myths of a lost mother star, a great conflagration, and a world tree or axis mundi that connected Earth to heaven are seen as global eyewitness accounts of this same event. The theory attempts to weave together comparative mythology, ancient art, and anomalous geological evidence into a single, catastrophic narrative that reshaped both our solar system and human consciousness. While mainstream astronomy dismisses this as impossible, citing the immutable laws of orbital mechanics and the lack of any physical evidence for such a recent rearrangement, the power of the Saturn myth lies in its emotional resonance. It offers a literal reading of our oldest stories, suggesting that the trauma of losing a stable sky is etched into the very bedrock of human culture. It asks us to look at the gas giant in our telescopes not as a distant, cold world, but as the fallen god of a forgotten age, the silent remnant of a time when heaven itself was a different and perhaps more comforting place. The Golden Age shattered in a celestial war, but one object from that chaos became a legend in its own right. Among the most fiercely debated theories in all of alternative cosmology is the claim that the planet Venus is not an ancient world, but a newborn terror from our own historical past. This is the Venus catastrophe theory, championed by psychoanalyst Immanuel Velikovsky in the 1950s. His book, Worlds in Collision, proposed a solar system so dynamic and violent it reads like mythology written in the stars. Velikovsky argued that around 3,500 years ago, a massive object was ejected from the gas giant Jupiter. This was not a gentle birth. It was a cataclysmic event that flung a giant, incandescent body into the inner solar system, a comet that would become the planet Venus. This newborn comet, with a long, glowing tail of gases, entered a chaotic, intersecting orbit that brought it into repeated, close encounters with Earth and Mars over centuries. According to Velikovsky, these near misses were not quiet astronomical events. They were global catastrophes that reshaped our planet and rewrote human history. As the comet Venus approached Earth, its immense gravitational pull would have caused worldwide earthquakes and tidal waves of biblical proportions. The electrical interaction between the two bodies, a key part of Velikovsky's thinking, could have generated massive electrical discharges seen as fire raining from the sky. The comet's tail, filled with hydrocarbons, could have rained down as a sticky, flammable substance, manna from heaven in some stories, a terrifying plague in others. He then pointed to a stunning array of ancient texts from cultures that had no contact with each other. The myths seem to tell the same story. Babylonian records describe the goddess Ishtar, associated with Venus, as a fearsome, bearded star that threatened the heavens. Egyptian texts speak of the celestial goddess Sekhmet bringing fire and pestilence. The Greek poet Homer called the morning star Venus a blazing comet. Most compellingly, Velikovsky highlighted the near-universal memory of a time when the day was miraculously lengthened. He connected this to the biblical story of Joshua commanding the sun and moon to stand still during a battle. If Earth's rotation was temporarily disrupted by the gravitational grip of a passing massive object, it could have created the perception of a prolonged day or night across different parts of the globe. After its encounters with Earth, the comet Venus, according to the theory, then interacted with Mars, disrupting its orbit and scarring its surface before finally settling into its current, nearly circular path around the Sun. The heat from its violent birth and close passages, Velikovsky claimed, explained why Venus has such a scorching surface temperature, a fact not confirmed until probes visited the planet decades later. The scientific backlash was immediate and ferocious. Astronomers like Carl Sagan led the charge, dismantling the theory point by point. The orbital mechanics were impossible, they said. A body ejected from Jupiter could not achieve a stable circular orbit so quickly. The energy required to stop Earth's rotation would vaporize the planet's crust. The idea that Venus was still hot from events a few thousand years ago violated the laws of thermal radiation. Velikovsky was labeled a pseudoscientist, and his publisher was pressured by the academic establishment. Yet, in a strange twist, some of his bold predictions later came true against all expectations of the time. He predicted, based on his electrical model, that Venus would be extremely hot. The scientific consensus in the 1950s was that Venus, shrouded in clouds, was a swampy, tropical world. When Mariner 2 probed Venus in 1962, it found a surface temperature hot enough to melt lead. He predicted that Venus would have a disturbed, anomalous rotation and possibly a cometary tail of hydrocarbons. Venus does rotate backwards extremely slowly, and later missions found its atmosphere rich in hydrocarbon compounds. These hits did not validate his entire narrative, but they forced a moment of pause. They highlighted how often scientific consensus can be confidently wrong. The Venus catastrophe theory, for all its likely inaccuracies, serves as a powerful reminder that our solar system's calm, clockwork appearance is a recent snapshot in a deep and possibly violent history. It challenges us to listen to the oldest stories not as mere superstition, but as potential eyewitness accounts to a sky in turmoil, a time when the gods were not metaphors but planets crashing through the heavens. The shadow of a wandering, vengeful world is a story older than civilization itself. Among the most persistent modern doomsday narratives is the tale of Nibiru, or Planet X, a rogue giant on a secret, elliptical orbit that will one day sweep through the inner solar system, triggering pole shifts, earthquakes, and the end of our world. This theory is a powerful fusion of fringe astronomy, misinterpreted mythology, and deep-seated distrust. Its origins are often traced to the writings of Zecharia Sitchin, who in the 1970s interpreted ancient Sumerian cuneiform tablets not as mythology, but as literal astronaut chronicles. He claimed they described a planet called Nibiru, home to an advanced race called the Anunnaki, which orbits our sun every 3,600 years on a long, slanted path. According to Sitchin, the Anunnaki came to Earth to mine gold and genetically engineered humanity as a slave race. The prophecy, embraced by many, is that Nibiru is due for its return, and its gravitational influence will bring global catastrophe. The idea gained terrifying momentum with the rise of the internet, where grainy images, shaky videos of a second sun, and claims of government cover-up spread like digital wildfire. Proponents point to natural disasters, strange animal behavior, and even the precession of the Earth's axis as proof of the approaching Titan's pull. They argue that space agencies like NASA are actively hiding its approach, editing it out of telescope images and silencing whistleblowers to prevent global panic. The astronomical reality, however, offers a firm and clear rebuttal. A planet large enough to cause the cataclysms described, often said to be several times the mass of Earth, would be an unmistakable beacon in our sky long before its arrival. Its gravitational influence would have been perturbing the orbits of the outer planets for centuries, effects that our precise orbital calculations would easily detect. Our network of space probes, from Voyager to New Horizons, and our fleet of Earth and space-based observatories map the solar system with incredible accuracy. An inbound planet of that size would be brighter than any star, visible to amateur astronomers everywhere, impossible to conceal. The term Planet X itself has a legitimate but very different scientific history. It was coined by astronomer Percival Lowell in the early 20th century as a placeholder for a theorized planet beyond Neptune, whose gravity might explain slight irregularities in Uranus's orbit. This search ultimately led to the discovery of Pluto in 1930, though Pluto was far too small to be the original Planet X. Today, astronomers do speculate about a possible Planet 9, a super-Earth in the distant Kuiper belt, as we discussed earlier. But its proposed orbit keeps it hundreds of times farther from the Sun than Earth is, and it poses no threat of entering the inner solar system. It is a sedate, distant object, not a celestial hammer. The cultural persistence of Nibiru, however, is more revealing than any astronomical fact. It taps into a profound human archetype, the destroyer god who returns at the end of a great cycle. It provides a singular, dramatic explanation for the anxiety of living in an unpredictable world, channeling fears of climate change, political instability, and pandemics into a tangible, cosmic villain. The alleged cover-up feeds a deep skepticism of authority, turning scientific institutions into villains in a cosmic conspiracy thriller. In a complex, data-saturated age, the simplicity of a single cause for all our troubles is perversely comforting. It means the chaos has a name, a schedule, and in the minds of believers, a group of elites who know the truth. This transforms the Nibiru myth from a failed prediction into a modern folklore, a mirror reflecting our timeless fear of the sky falling and our instinctive distrust of those who tell us it will not. The fear of a hidden destroyer from the sky finds a chilling echo in a theory grounded not in myth but in astrophysics. Our galaxy's serene spiral is an illusion, for at its heart lies a sleeping dragon. The supermassive black hole Sagittarius, a star, is mostly quiet, but evidence suggests it has awoken with terrifying violence in the past. The galactic superwave hypothesis proposes that these awakenings are not random, but part of a deadly cosmic rhythm. Every 10 to 15 million years, a massive influx of matter, perhaps a shredded star or a collapsing gas cloud, plunges into the galactic core. This feast triggers a cataclysmic explosion, a quasar-like outburst that does not fire a narrow beam, but a spherical tsunami of high-energy gamma rays and cosmic rays. This wave expands outward at nearly the speed of light, a silent, invisible front of radiation that sweeps through the galactic disk. When such a wave washes over a solar system, the consequences are apocalyptic. The initial gamma-ray pulse would strip away planetary atmospheres and bathe surfaces in sterilizing radiation. But the more insidious and lasting effect comes from the cosmic rays, atomic nuclei accelerated to near light speed. As this dense wave of particles crashes into our solar system, it violently compresses the Sun's protective magnetic bubble, the heliosphere. For a period lasting perhaps a few thousand years, Earth and the entire inner solar system would be exposed directly to the harsh interstellar medium. Our planet's own magnetic field would be bombarded, leading to intense geomagnetic storms and auroras that light up the entire sky, day and night. The real planetary shift, however, comes from the atmosphere. The barrage of cosmic rays would dramatically increase cloud formation. Cosmic rays act as seeds for cloud condensation nuclei, literally helping to weave the blanket of the sky. A sustained surge would create a denser, more reflective global cloud cover. Sunlight that would normally warm the surface is bounced back into space. The result is a rapid, severe global cooling, a plunge into an ice age. Proponents of this theory, like physicist Paul Laviolette, point to geological layers as evidence of these periodic deluges. They examine ice cores from Greenland and Antarctica, which act as frozen history books, at certain depths corresponding to times of known extinction events and glacial advances. Scientists find sharp spikes in concentrations of cosmic dust and specific isotopes like beryllium-10 and nitrogen-14. These are the forensic signatures of a cosmic ray event, the fallout from a galactic storm. One of the most compelling alignments is with the Pleistocene extinction event around 12,800 years ago, which wiped out megafauna like mammoths and saber-toothed cats. A layer of sediment from that time, found across North America and Europe, shows high levels of iridium, nanodiamonds, and soot, markers of an extraterrestrial impact. But the superwave theory offers a different, or perhaps complementary, trigger. A galactic wave could have destabilized the Oort cloud, sending a shower of comets inward just as it chilled the climate, a 1-2 punch of cosmic catastrophe. The hypothesis reframes our place in the cosmos. We are not merely orbiting a quiet star in a peaceful suburb of the Milky Way. We are sailing on a sea that is periodically churned by titanic eruptions from a monster at the galactic core. Our climate, our very survival as a species, may be subject to a timer we cannot see, set by the digestion of a black hole 26,000 light-years away. It suggests that the great cycles of ice and extinction on our planet are not solely driven by subtle wobbles in Earth's orbit, but may be written in the violent heartbeat of the galaxy itself. The myth of Nibiru is a story about stories, revealing how easily ancient texts can be twisted into modern prophecy. Zachariah Sitchin did not just translate Sumerian tablets, he wove a new cosmic epic from them. A polyglot who claimed fluency in ancient languages, Sitchin interpreted the cuneiform symbols not as the poetry and mythology scholars recognize, but as literal astronaut records. He saw the god Marduk not as a deity, but as a planet, Nibiru, with a vast 3,600-year orbit. The Anunnaki were not gods of the underworld, but flesh and blood extraterrestrial miners who genetically engineered Homo sapiens as a labor force. This narrative was a masterstroke of syncretism, blending space-age fascination with ancient mystery into a single, seductive origin story. It offered a powerful alternative to both religious creationism and scientific evolution, replacing a distant, unknowable god with advanced, if flawed, alien engineers. The prophecy was built in, a ticking clock of return. When this rogue planet came back, the masters would return and chaos would reign. This provided a perfect narrative engine for doomsday culture, giving apocalyptic fear a specific name and a scheduled date, one that has been continually pushed forward as each predicted arrival passes without event. The myth's persistence is not despite scientific rebuttals, but because of them. Each dismissal from NASA or an astronomer is folded back into the lore as proof of the cover-up. Grainy photos of lens flares are presented as the hidden planet, its light supposedly filtered out by government agencies. The internet became the perfect ecosystem for this idea, a place where evidence is subjective, authority is distrusted, and algorithms connect the fearful into self-reinforcing communities. It transforms from an astronomical claim into a cultural symptom, a vessel for anxieties about climate change, societal collapse, and institutional deceit. In a complex, data-saturated world, the simplicity of a single, hidden cause for all our troubles is perversely comforting. It means the chaos is not random. It has a villain, a schedule, and a secret group of elites who know the truth. Nibiru is the ultimate modern myth, a dark star born not in a nebula, but in the human need for narrative, reflecting our oldest fear that the sky one day will truly fall. From the chaos of quantum possibilities, a single, stable world emerges. How does the blurry quantum realm, where particles exist in multiple states at once, give rise to the solid, objective reality we all agree upon? A compelling answer lies in a theory that borrows from biology's greatest idea. Quantum Darwinism proposes that our classical reality is not a random selection, but the result of a survival of the fittest among quantum states. In the bizarre quantum world, a particle like an electron can be in a superposition, spinning both clockwise and counterclockwise simultaneously. This fragile state exists only in isolation. The moment it interacts with its environment, even with a single photon of light or a stray air molecule, something profound happens. The superposition is probed, tested, and ultimately, most of its possibilities are erased. But not all. According to quantum Darwinism, certain quantum states are more robust than others when faced with this environmental interaction. They are the fittest states. These resilient states get copied over and over again into the surrounding environment. Imagine dropping a red dye tablet into a still pond. The dye disperses in a unique pattern, but the information that the dye was red is replicated in every single water molecule it touches. Anyone sampling the water from any part of the pond would deduce the dye was red. In quantum Darwinism, the environment is that pond. A quantum system interacts with countless particles in its surroundings. Only the most stable, redundant states of that system get imprinted onto those environmental particles. These multiple, scattered imprints become the consensus reality. So, when you look at a chair, you are not directly observing the quantum particles of the chair itself. You are catching the echoes. Your eyes are sampling the photons of light that have bounced off the chair, photons that have been imprinted with the chair's stable, classical properties, its position, its shape, its color. Those properties were selected because they were the ones durable enough to be copied billions of times into the environment. The other, more fragile quantum possibilities simply died out, leaving no trace for you to detect. This process explains why we all see the same chair. The environment has been plastered with countless identical copies of the same information. Different observers, whether a person, a camera, or a scientific instrument, all access these public records, leading to an agreement on objective facts. It is not that consciousness causes the wave function to collapse, as in older interpretations. Instead, reality becomes objective through a form of quantum natural selection, where the fittest states proliferate until they become the only story the environment tells. This turns the emergence of the classical world from a mystery into a dynamic, physical process. We do not live in a special, collapsed version of reality. We live in the version that was strong enough to survive, to replicate, and to fill the world with consistent evidence of its existence. The universe, in this view, is a vast archive, and everything we perceive is a surviving record, copied so many times it has become the truth. The universe's archives are written in surviving quantum states, but to read them across the stars, we would need an engine of impossible power. Enter the most audacious propulsion concept ever conceived, a vessel not powered by fire or light, but by controlled annihilation. The Black Hole Starship is a theoretical spacecraft that would use a microscopic, artificial black hole as its power plant, offering the key to journeys across the galaxy. This is not about falling into a black hole, but about putting one in a cage and harvesting its final, furious scream. The principle relies on one of Stephen Hawking's greatest discoveries, Hawking radiation. A black hole is not truly black. It emits a faint glow of particles due to quantum effects at its event horizon. For a colossal, stellar mass black hole, this radiation is negligible, a whisper lost in the cosmic background. But for a tiny black hole, the story is dramatically different. The smaller a black hole is, the hotter it glows and the faster it evaporates. A black hole with the mass of a small mountain would shine with the brightness of 1,000,000 nuclear reactors, emitting its entire existence as energy in just a few years. The proposal is to create, or perhaps capture, a black hole of precisely this scale, about the mass of a large asteroid compressed into a proton-sized point. Encase this raging singularity in an electromagnetic containment field, a perfect mirror sphere that captures every ounce of its Hawking radiation. One side of this sphere is open, forming a nozzle. The intense radiation blasting against the closed end of the chamber creates thrust, pushing the entire spacecraft forward. The numbers are staggering. Such an engine could, in theory, accelerate a massive ship to a significant fraction of the speed of light, enabling voyages to nearby stars within a human lifetime. The energy density is unparalleled, turning the mass of an asteroid into pure propulsion with near-perfect efficiency. but the engineering challenges are, to put it mildly, cosmic. First, you must create or obtain the black hole. One speculative method involves focusing unimaginably powerful gamma-ray lasers into a single, infinitesimal point, crushing spacetime itself into a singularity. The energy required is far beyond our current capabilities, perhaps requiring the total output of a star. Alternatively, we might search for and capture a naturally occurring primordial black hole of just the right size, a cosmic fishing expedition of incredible precision and danger. Then comes the containment problem. You are essentially trying to bottle a sun that is also a gravitational singularity. The electromagnetic cage must be flawless, for if the black hole touches the walls of its prison, it would begin to consume the ship, growing larger and cooler, eventually becoming useless as an engine and ultimately devouring the entire vessel. The containment system would need to be actively stabilized, constantly adjusting to the black hole's movements and the changing thrust demands. Navigation becomes an exercise in existential precision, a constant balancing act on the edge of oblivion. Yet, if it could be built, the rewards redefine possibility. A black hole starship would be a self-contained universe, its power source independent of external fuel. As the black hole evaporates, the ship gets lighter, allowing for even greater acceleration. The crew would live in a habitat ring at the front of the ship, shielded from the lethal radiation pouring out of the engine by the ship's own mass and sophisticated barriers. They would watch as stars ahead blue shifted and stars behind red shifted into darkness, the galaxy itself warping around them. This is not merely a faster engine. It is a transformation of the ship into a temporary, artificial star, a mobile point of creation and destruction that carries its own dying sun within it. The concept forces us to confront the ultimate technological ambition, to not just harness nature, but to forge and command one of its most fundamental and terrifying phenomena. It suggests that the path to the stars may not lie in taming fire, but in learning to dance with darkness, using the final sigh of a manufactured cosmos to sail the endless night. The black hole starship's engine is a manufactured death, but perhaps every death in the cosmos is secretly a birth. The idea that our entire universe is the interior of a black hole is not just a poetic metaphor. It is a serious cosmological hypothesis that redefines the meaning of creation and destruction. In this view, the Big Bang was not a singular explosion from nothing, but the violent rebound of matter that collapsed in another reality. Our cosmos exists on the other side of an event horizon, a cosmic womb hidden within the gravitational tomb of a parent universe. The mathematics is startlingly symmetrical. The equations of general relativity that describe the crushing singularity at the heart of a black hole bear an uncanny resemblance to those describing the expanding singularity of the Big Bang. Both are points of infinite density where our known laws of physics break down. This symmetry led physicists like Nikodem Poplawski to propose a breathtaking model. In a much larger parent universe, a colossal amount of matter collapses under its own gravity, forming a supermassive black hole. But at the very moment of that collapse, at the point of maximum compression, something extraordinary happens. The matter does not simply vanish into a dead-end singularity. Instead, it rebounds. The intense gravitational energy fuels a new expansion, birthing a new space-time continuum with its own laws and dimensions, all contained within the event horizon of the parent black hole. Think of it as a cosmic Russian nesting doll, but one where each doll is an entire universe. From the outside, in the parent cosmos, the object is a black hole, a dark sphere from which nothing escapes. But from the inside, for the beings born within it, that black hole is their entire expanding universe. They perceive no boundary, only an endless cosmos stretching out from a hot, dense beginning. This elegantly solves several profound puzzles. It provides a physical origin for the Big Bang without needing a before. The parent universe's black hole could have formed from natural processes, giving our cosmos a causal, if inaccessible, history. it also offers a potential solution to the black hole information paradox. The information swallowed by a black hole is not lost, it becomes the initial conditions, the very seed from which a new universe sprouts. Every star and galaxy in our sky could be the transformed, reorganized data of whatever fell into that progenitor singularity. The implications become even more staggering when you look inward into the dark hearts of our own cosmos. If our universe was born from a black hole, then every black hole that forms within our universe could, in turn, be giving birth to a new cosmos of its own. When a massive star dies and collapses, or when two black holes merge, the resulting singularity might not be a final grave, it could be a cosmic egg. Inside that point of infinite density, the conditions might be ripe for another Big Bang, initiating a new spacetime bubble completely disconnected from our own. Each black hole in our sky could be a portal to an entire other reality, a universe with its own unique physical constants, its own dimensions of space and time, and perhaps its own forms of life. This creates a fractal cosmology, an endless cascade of creation where universes beget universes in an infinite chain of cosmic reproduction. Our entire history, from the first stars to the rise of civilizations, would be playing out inside a black hole that exists in a parent universe, which itself is inside another black hole, and so on, backwards and forwards forever. There is no top-level reality, only an infinite regression of cosmic nesting. This theory transforms black holes from monsters into mothers. The darkest objects in our universe become the brightest cradles of new existence. It suggests that death on the grandest scale is not an end, but a metamorphosis, a recycling of reality into new forms we can never visit or communicate with. The event horizon is not a wall of oblivion, but a one-way curtain between generations of cosmos. While this idea is difficult, if not impossible, to test directly, it offers a profound and strangely beautiful vision of eternity. It means that even as our own universe expands toward a cold, dark fate, within every black hole that forms from its dying embers, a new fire is being lit, a new story is beginning in a reality forever hidden from our own. We are not just living in a universe, we are living inside a legacy, one link in an infinite chain of cosmic rebirth. This infinite chain of cosmic rebirth still requires a witness, an observer, to give it meaning. But what if the observer is not merely a product of the universe, but its very source? This is the ultimate inversion of our common sense reality. The idealist claim that consciousness is not an emergent property of complex brains, but the fundamental ground of all existence. Matter, energy, space, and time are not the primary reality. They are constructs within a vast, universal mind. In this view, the physical cosmos is not a machine that somehow generated awareness. It is a dream, a thought, a persistent structure within consciousness itself. The roots of this idea are ancient, found in Eastern philosophies and the works of thinkers like George Berkeley, who argued that to be is to be perceived. But in the 20th century, this metaphysical idea found a strange and compelling echo in the baffling results of quantum physics. The central mystery of the quantum world is the role of the observer. In the famous double-slit experiment, a particle behaves like a spread-out wave of possibilities until it is measured. At that moment, the wave function collapses and the particle assumes a definite location. The burning question has always been, what constitutes a measurement? Does it require a conscious being to look at the data? The idealist interpretation answers with a resounding yes. Consciousness is the catalyst that transforms possibility into actuality. Without an observer, reality remains in a fuzzy, unrealized state of potential. This does not mean you personally are dreaming up the stars, but that a universal field of consciousness, of which our individual minds are localized expressions, is doing the dreaming. The entire universe exists because it is being observed by the cosmic mind, and our own perceptions are tiny fragments of that grand awareness. This perspective finds support in a curious feature of our cosmos, the anthropic principle. Scientists have long been puzzled by the fact that the fundamental constants of nature seem exquisitely fine-tuned for the existence of life. The strength of gravity, the nuclear forces, the cosmological constant. If any of these values were altered by even a minuscule fraction, atoms would not hold together, stars would not burn, and complex chemistry would be impossible. The universe would be barren. The strong anthropic principle, in its idealist reading, suggests a startling explanation. The universe is tuned for observers because observers are required to bring it into being. In a sense, the universe fine-tuned itself for the emergence of consciousness because consciousness is the reason for its existence. It is a closed loop, a self-consistent story where the observer and the observed are two sides of the same coin. Imagine a video game world. The mountains, rivers, and characters are not made of physical material. They are made of information, of code. They only render, they only become solid and interactive when the player's avatar is near. The distant parts of the map remain in a low-resolution state of potential. In the idealist view, our physical reality operates on a similar principle, with consciousness as the player. The moon is not a definite rock in a definite orbit when no one is looking at it or thinking about it or measuring its gravitational pull. It exists in a probability cloud, a set of potential states, until the act of observation calls it forth. This solves the quantum measurement problem by placing consciousness outside the physical system as the fundamental reality that collapses the wave function. It also offers a profound answer to the question of why there is something rather than nothing. There is something because there is consciousness. Experience is the primary datum, the one thing we cannot doubt. Everything else, from the chair you are sitting on to the most distant galaxy, is an inference, a model built within that experience. The idealist universe is not a cold, empty mechanism. It is a living, conscious thought, and we are the places where that thought becomes aware of itself. This cyclical rebirth could be more than just a reshuffling of cosmic dice. The ultimate cosmic return is not a new universe, but the exact same one, replayed note for note. The theory of the time loop universe is rooted in a profound mathematical concept called Poincaré recurrence. It states that in a closed system with a finite amount of energy and a finite volume, every possible arrangement of particles will eventually recur given enough time. If the universe is such a system, then every atom, every star, and every conscious thought is destined to return to its exact present arrangement. This is not a similar universe or a universe where you live a similar life. It is this universe repeating itself identically in an infinite loop. The scale of time involved is almost a parody of eternity. For our observable universe to randomly fluctuate back to its current state, physicists estimate a timescale so vast it makes the age of our cosmos look like a single blink. We are talking about a number with more zeros than there are particles in the universe. Yet in a truly eternal timeline, even that unimaginable number is just a moment. Given infinite time, every finite probability becomes a certainty. This means that after the last black hole evaporates and the cosmos reaches a state of maximum entropy, a featureless sea of low-energy particles, it will not stay that way forever. Through sheer random chance, quantum fluctuations will eventually assemble a configuration identical to the one that existed at the moment of the Big Bang. The entire cosmic drama will play out again in precisely the same way. The sun will form, Earth will coalesce, life will evolve, and you will be born. You will make every single choice you have ever made, experience every joy and every sorrow, and watch this very video all without any memory of the previous cycle. It will feel like the first and only time because for the consciousness in that cycle it is. The philosophical weight of this idea is crushing and liberating in equal measure. It suggests that free will and destiny are the same thing. You are both the author of your life and an actor perfectly reciting an eternal script. every mistake is fated to be repeated, but so is every triumph. Every moment of love, of discovery, of connection is not lost to time. It is inscribed forever in the loop, guaranteed to happen again. This transforms the heat-death of the universe from a final ending into an intermission, a long, dark pause before the curtain rises on the same play. The universe forgets so that it can remember itself again. While this is a logical consequence of certain classical physics models, our modern understanding introduces complications. If the universe's expansion continues to accelerate due to dark energy, it may never be a truly closed, finite system. It could expand forever into an infinite, dilute void, making a precise recurrence statistically impossible. Yet, some cyclical models find ways to incorporate the concept, suggesting that each bounce or rebirth, while not perfectly identical, could be so statistically similar as to be indistinguishable to any observer within it. The time loop universe asks the ultimate question about meaning. If your life is on infinite repeat, does it rob your actions of significance, or does it grant them a kind of eternal weight? You are living a story that has no beginning and no end, only chapters. In that light, this moment right now is not fleeting, it is permanent. You are forever sitting here listening to this idea in an endless cosmic echo. That same holographic principle, born from the study of black holes, reveals an even deeper secret about the nature of reality. The paradox that sparked this idea is one of physics' greatest puzzles, the black hole information paradox. When anything, a book, a star, even a person falls past a black hole's event horizon, it is lost to our universe. According to Einstein's classical theory, that object is crushed into the singularity, and all the intricate information about what it was made of, its shape, its history, is erased forever. The black hole only gains mass, charge, and spin. This is a profound problem because quantum mechanics has a sacred rule: information can never be destroyed. It can be scrambled, hidden, or transformed, but it must always, in principle, be recoverable. So, where does the information go when it falls into a black hole? The holographic principle provides a breathtaking answer. The information is not lost inside the three-dimensional pit. It is not crushed at all. Instead, it is perfectly preserved, painted onto the two-dimensional surface of the event horizon itself. Imagine you are about to throw an encyclopedia into a fire. In a normal fire, the pages burn, the ink vaporizes, and the information is lost in smoke and heat. But a black hole is not a normal fire. As the encyclopedia crosses the horizon, something miraculous happens. Its three-dimensional information, the weight of the paper, the curve of the binding, the words on every page, is instantly translated into a two-dimensional code. This code is written in the most microscopic units possible, Planck-scale pixels on the surface of the black hole. The event horizon becomes a vast, cosmic hard drive, with every bit of information from the fallen object meticulously recorded on its spherical shell. This is not a metaphor, it is a direct consequence of the mathematics of black hole thermodynamics. The entropy of a black hole, which is a measure of its hidden information, is proportional to the area of its event horizon, not its volume. This was the crucial clue discovered by Jacob Bekenstein and later expanded by Stephen Hawking. It told physicists that the maximum amount of information any region of space can contain is not related to how big it is inside, but to how much surface area it has. The interior volume is an illusion, a projection. The true reality, the data, lives on the boundary. This transforms the black hole from a cosmic shredder into the ultimate archival system. The fiery demise of the encyclopedia is an illusion for anyone outside. From our perspective, the information is safely stored, albeit in a form we could never directly read. This resolution to the information paradox suggests something staggering about our own reality. If a black hole, the most extreme object in the universe, can encode a three-dimensional world on a two-dimensional surface, then perhaps our entire universe, which from a certain vantage point looks like the interior of a black hole, is doing the same. The three-dimensional world we move through, with its galaxies and oceans and living beings, might be a magnificent projection from a two-dimensional film of information at the cosmic horizon. The solidity we feel, the depth we see, could be a grand and convincing holographic illusion, with every event in the cosmos simply a piece of data being processed on the ultimate screen. Yet within that cosmic echo, another theory quietly weaves the fabric of reality from threads of pure geometry. While string theory imagines tiny vibrating strings, loop quantum gravity proposes a universe built from woven loops. This is a radically different approach to the holy grail of physics, a theory of quantum gravity that seeks to merge Einstein's general relativity with quantum mechanics by reimagining the very stage on which the universe performs. In this view, space itself is not a smooth, continuous backdrop. It is granular, woven from an unimaginably dense fabric of tiny, one-dimensional loops. These loops at the Planck scale link together to form a dynamic, ever-changing network called a spin network. Picture space not as an empty container, but as a vast three-dimensional spiderweb where each connection is a fundamental thread of reality. Time in this framework is not a separate river flowing through this web. It emerges from the evolution of the spin network's connections. The web changes, it updates, and that sequence of changes is what we perceive as the passage of time. This means that at the most fundamental level, there is no space and time as we know them, only a network of relationships, a cosmic knot of information from which our familiar four-dimensional reality crystallizes. The most profound consequence of this loop quantum cosmology, the application of these ideas to the universe as a whole, is what it does to the Big Bang. In the Standard Model, the Big Bang is a singularity, a point of infinite density where all our equations break down and we lose any ability to describe what happened. It is the ultimate edge of knowledge. Loop quantum gravity erases that edge. Because space is quantized into these tiny loops, it cannot be compressed to an infinitely small point. There is a smallest possible volume, a quantum grain to the cosmos. As we rewind the cosmic film back toward the beginning, the density and curvature of spacetime increase enormously, but they do not become infinite. Instead, the quantum geometry reaches a maximum density and then, like a spring compressed to its limit, it rebounds. The collapse reverses into an expansion. This is the big bounce. The universe before the bounce could have been a contracting phase of a previous cosmic cycle, collapsing under its own gravity until quantum effects took over and sparked our own expansion. Our Big Bang was not a beginning from nothing, but a transition from a prior cosmic phase. This removes the terrifying singularity, replacing a wall of ignorance with a bridge to a potentially eternal history. The theory makes a startling prediction about that moment of transition. The quantum repulsion that causes the bounce would have imprinted a specific signature on the oldest light in the universe, the cosmic microwave background. It would have slightly suppressed the very largest scale fluctuations, leaving a subtle but potentially detectable fingerprint in the way galaxies are clustered across the sky. Scientists are now scouring data from telescopes, looking for this faint echo of a bounce, a whisper from the other side of our origin. Loop quantum gravity presents a universe that is not born from a mysterious fireball, but from a quantum tremor in an eternal fabric. It suggests that the cosmos breathes and that our entire existence is the expansion phase of one cosmic breath in an endless cycle. In this vision, the universe is not a one-time event, but a resilient, self-renewing entity, with its space-time woven from loops so small they define the very meaning of here and now. The ultimate goal of all this searching is not just another theory, but the final one. For centuries, physics has operated with two separate rulebooks. The first, general relativity, masterfully describes the universe on its grandest scales, the dance of galaxies and the curvature of spacetime by mass and energy. The second, quantum mechanics with uncanny precision, governs the bizarre and probabilistic world of the atom and its subatomic constituents. Both are spectacularly successful in their own domains, yet they are fundamentally, stubbornly incompatible. When their equations are forced to meet, such as at the center of a black hole or the first instant of the Big Bang, the result is nonsense, infinities that signal a complete breakdown of our understanding. This schism is the deepest crack in the foundation of modern science, and bridging it is the quest for a theory of everything. This is not merely a desire for neatness. It is the pursuit of a single, elegant framework that unifies all four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces, and describes all known particles as manifestations of something more fundamental. It seeks to answer the question of what spacetime itself is made from, and to provide a coherent narrative for the universe from its first quantum tremor to the vast cosmic structures we see today. Two titanic candidates dominate this quest, each approaching the problem from a diametrically opposite direction. The first is string theory. It proposes that at the most fundamental level, the universe is not composed of point-like particles. Instead, the basic ingredients are unimaginably tiny, vibrating loops or strands of energy, strings. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, a single fundamental string can vibrate in different modes to produce the entire zoo of particles we observe. The electron is one vibrational pattern, the quark is another, the photon, carrier of light, is yet another. In this symphony of strings, even gravity finds its player, a hypothetical particle called the graviton. The elegance is profound, but it comes at a staggering cost. The mathematics of string theory only works if the universe has more than the 3 spatial dimensions we experience. It requires, depending on the version, 10 or 11 dimensions. The extra dimensions, the theory suggests, are curled up or compactified on a scale so small we could never perceive them directly, like a garden hose appearing as a one-dimensional line from a distance. The challenge, however, goes beyond hidden dimensions. String theory is not one theory, but a vast landscape of possible solutions, perhaps 10 to the 500 different versions, each corresponding to a universe with different physical laws and constants. This multiverse of theories makes it incredibly difficult to extract unique, testable predictions for our specific universe. We are left with a framework of breathtaking beauty and scope, but one that risks being untestable, a philosophy of mathematics rather than empirical science. The second great contender is loop quantum gravity. We have already seen how it weaves space from loops. Unlike string theory, it does not try to unify all forces by adding extra dimensions. Instead, it takes Einstein's general relativity and quantizes it directly, applying the rules of quantum mechanics to the fabric of spacetime itself. In this view, gravity is not a force transmitted by a particle, but a consequence of spacetime's discrete quantum structure. Space is not smooth, but a fabric of finite, woven loops. This approach keeps us firmly in a 4-dimensional world and makes a bold, testable prediction about the beginning of our cosmos, the Big Bounce. Yet, loop quantum gravity has its own steep challenges. While it beautifully quantizes gravity, it has so far struggled to seamlessly incorporate the other 3 fundamental forces and the particles of the standard model of particle physics within its framework. It risks being a theory of gravity alone, not of everything. The quest, therefore, stands at a fascinating impasse. String theory starts with particles and forces and seeks to include gravity, but may require a landscape of universes. Loop quantum gravity starts with gravity and the geometry of space, but must still find room for matter. Other, more speculative ideas exist, like causal dynamical triangulation, which builds spacetime from tiny geometric blocks, or the amplituhedron, a geometric object that simplifies particle interactions but has yet to incorporate gravity. So what would a successful theory of everything actually mean for us? It would be the final chapter in a story that began with Newton unifying the motion of apples and moons. It would reveal the universe not as a collection of separate phenomena, but as a single, coherent mathematical expression. It could tell us what happened at the absolute beginning, whether our universe is one of many, and whether time truly had a start. It would transform black holes from paradoxical monsters into well-understood laboratories of quantum gravity. Most philosophically, it would complete our map of reality, from the smallest conceivable grain of spacetime to the entire cosmic expanse. Yet, even a complete theory of everything may not be a theory of everything. It would describe the fundamental laws and particles, but it would not necessarily predict the weather next Tuesday, the evolution of life, or the nature of consciousness. These are emergent phenomena, complex patterns that arise from the interaction of countless simpler parts, much like the wetness of water emerges from molecules that are not themselves wet. The ultimate theory would provide the foundational rules, but the rich, messy, beautiful story of our universe and our place within it would still be written by the consequences of those rules, playing out over billions of years. The search continues, a testament to our deepest drive to understand the stage upon which all these bizarre and wonderful theories dance. We have journeyed through a cosmos where nothing is as it seems. From the unsettling possibility that we live in a simulation or a hologram, to the cosmic dread of the great filter and the dark forest, each theory has stretched the fabric of our understanding to its breaking point. We have explored universes within black holes, cyclical bounces, and phantom energies that could rip everything apart. We have confronted the idea that our own moon might be hollow, that planets might have recently warred in our skies, and that our consciousness could be a quantum phenomenon or the very source of reality itself. This is not a catalogue of answers, but a map of the profound questions that define the cutting edge of human thought. These 50 theories are not mere science fiction. They are the logical, if extreme, extensions of our best mathematics and observations, daring us to think bigger and question deeper. They remind us that science's greatest power is not in confirming what we already know, but in systematically exploring everything we do not. So, which idea reshaped your reality the most? Was it the cosmic zoo, the Boltzmann brain, or the universe as a neural network? Let us know in the comments below. Share your favorite theory or your own bizarre cosmic idea. If this journey through the edges of understanding fascinated you, show your support with a like and subscribe for more explorations into the mysteries of our incredible universe. The final frontier isn't just space, it's the limitless landscape of the human